Imagine staring into the vast emptiness of space and seeing something that shouldn't exist, a single point of blinding light that, upon closer examination, turns out to be two. But they're not just any 2 points of light. They're double quasars, one of the rarest and most mind-bending celestial phenomena in the universe. They defy expectations, challenge our understanding of physics, and may even hold clues to some of the biggest mysteries in cosmology. How can two of these cosmic monsters appear so close together? Are they actually separate, or is something even weirder going on? And what do they reveal about the fabric of spacetime itself? Double quasars aren't just a curiosity, they're a key to unlocking the secrets of the early universe. To understand them, we need to dive deep into what quasars actually are. A quasar is one of the most extreme objects in existence. It's a supermassive black hole millions to billions of times the mass of the Sun, sitting at the center of a distant galaxy, and devouring everything around it. But unlike a normal black hole, which is usually invisible, a quasar is surrounded by an accretion disk, a swirling, chaotic inferno of gas and dust that spirals toward the black hole, heating up to billions of degrees and blasting out energy. Quasars shine with the brightness of a trillion stars, sometimes outshining their entire host galaxy. And here's the wild part: they're so far away that the light we see from them has been traveling for billions of years. When we look at a quasar, we're looking back in time to the early universe. Now, if a single quasar is already this extreme, imagine seeing two right next to each other. That's what a double quasar is, two of these cosmic beacons appearing in close proximity. But why? There are two main explanations, and both are mind-blowing in their own way. The first possibility is that these quasars are part of a pair of merging galaxies, each with its own supermassive black hole. As the galaxies collide, their central black holes form a binary system, eventually spiraling toward each other before merging in a titanic event that sends gravitational waves rippling through space. These systems are incredibly rare, but they provide a glimpse into how galaxies grow and evolve over cosmic timescales. The second possibility is even stranger: gravitational lensing. This is a phenomenon predicted by Einstein's general theory of relativity, where massive objects like galaxies or black holes warp the fabric of spacetime. If a massive galaxy sits directly between us and a distant quasar, its gravity can bend and magnify the quasar's light, creating the illusion of two separate quasars. In reality, we're seeing two distorted images of the same object, separated by an apparent distance in the sky. This effect has allowed astronomers to measure the expansion of the universe, detect invisible dark matter, and even test the limits of Einstein's theories. So how do astronomers tell the difference between a real double quasar and a gravitationally lensed one? It's not easy. They use powerful telescopes like the Hubble Space Telescope and the Very Large Telescope to analyze the light coming from these objects. If the quasars have identical spectra, meaning their light contains the same unique fingerprint of elements, it's likely a lensed quasar. But if they show slight differences in their properties, they're probably a true binary quasar system. One of the most famous double quasars ever discovered is QSO 0957 plus 561, the first example of gravitational lensing ever found. Back in the 1970s, astronomers spotted what looked like two identical quasars close together. After careful analysis, they realized they were actually looking at two images of the same quasar, its light bent and duplicated by an intervening galaxy. This discovery was a huge breakthrough, proving that gravitational lensing wasn't just a theoretical prediction, it was a real, observable effect. But the search for true binary quasars continued. In recent years, astronomers have found several convincing cases of actual quasar pairs, some of them so close that their host galaxies are visibly merging. These systems give us a rare glimpse into the chaotic process of galaxy evolution, showing us what happens when two supermassive black holes are on a collision course. The eventual merger of these black holes is one of the most violent events in the universe, generating powerful gravitational waves that ripple across space. And here's where things get even more interesting. Double quasars could be a missing link in understanding how supermassive black holes grow. The biggest black holes in the universe, those with masses of billions of suns, must have formed through a series of mergers, but catching them in the act is incredibly difficult. Binary quasars might be the key to solving this puzzle, showing us how these cosmic giants come together over billions of years. Astronomers are now using the latest technology, including artificial intelligence, to hunt for more double quasars. The Vera C. Rubin Observatory, set to come online soon, will scan the entire sky and could uncover thousands of new candidates. Future space telescopes like the James Webb Space Telescope are also expected to provide detailed observations, revealing even more about these enigmatic objects. But there's still so much we don't know. How common are double quasars? What role do they play in shaping galaxies? Could some of them even be harboring the elusive intermediate mass black holes that astronomers have been searching for? The universe is full of unanswered questions, and double quasars might be holding some of the most exciting answers. And then there's the biggest mystery of all: what happens when two quasars finally merge? Does their combined black hole become an even more powerful quasar, or does the system collapse into darkness? Some models predict that these mergers could briefly create ultraluminous objects known as hyperquasars, blasting out energy at unprecedented levels before fading away. Others suggest that the final stages of a quasar merger could trigger new bursts of star formation in their host galaxy, reshaping it in unexpected ways. The more we study double quasars, the more we realize that they are far more than just a cosmic oddity. They are windows into the past, laboratories for testing physics, and stepping stones toward answering some of the deepest questions about our universe. We are just beginning to unravel their secrets, and with every new discovery, the universe becomes a little stranger, and a lot more fascinating. The discovery of double quasars is not just an astronomical curiosity, it's a doorway into understanding the fundamental forces shaping our universe. Each new observation adds a piece to a puzzle spanning billions of years, revealing secrets about galaxy formation, black hole evolution, and the very nature of spacetime. But as with any great mystery, every answer leads to more questions. One of the biggest challenges in studying double quasars is their sheer rarity. Astronomers estimate that for every 10,000 quasars, only a handful are true binaries. This means that finding them is like searching for a single grain of sand on an entire beach. The reason for their scarcity is tied to the nature of galaxy mergers. While galaxy collisions are common in the grand scale of cosmic time, the process takes hundreds of millions, sometimes even billions, of years. During this slow dance, supermassive black holes drift toward each other, interacting through complex gravitational forces. But only in a brief window of time, when the two black holes are close enough and actively accreting material, do they both shine as quasars simultaneously. Catching this fleeting phase is incredibly difficult. But when astronomers do find them, the implications are massive. These objects don't just help us understand how black holes merge. They also provide a way to test some of the most fundamental theories in physics. For example, binary quasars are crucial in studying gravitational waves, the ripples in spacetime predicted by Einstein's general theory of relativity. While modern observatories like LIGO and Virgo have already detected gravitational waves from smaller black hole mergers, the merging of supermassive black holes is on an entirely different scale. These events would create gravitational waves so massive that they could only be detected with specialized space-based observatories, like the upcoming LISA, Laser Interferometer Space Antenna. Studying double quasars helps us predict when and where such events might occur, guiding future missions designed to observe these powerful cosmic ripples. Another mind-bending aspect of double quasars involves their effect on the space around them. Quasars are already some of the most energetic objects in the universe, capable of shaping entire galaxies through their powerful outflows of radiation. But when two quasars interact in close proximity, their combined forces create a chaotic environment. The immense gravitational pull of both black holes warps the space around them, creating distortions that can be observed in the motion of nearby stars and gas clouds. Some simulations suggest that when two quasars are close enough, their competing gravitational forces can twist and stretch the fabric of their host galaxies, creating unusual structures like tidal tails, star-forming rings, and even distorted jets of plasma stretching for thousands of light years. One of the most fascinating aspects of double quasars is how they interact with dark matter, the mysterious, invisible substance that makes up most of the universe's mass. Quasars act like cosmic lighthouses, illuminating the otherwise unseen regions of space where dark matter is thought to exist. When two quasars exist in the same region, their combined energy can help reveal the distribution of dark matter around them. This is particularly useful for gravitational lensing studies, where astronomers use the warped light from quasars to map the hidden structure of dark matter. Some theories even suggest that studying double quasars could help us refine our understanding of dark energy, the force responsible for the accelerated expansion of the universe. And then there's the question of what happens in the final moments before two quasars merge. When two supermassive black holes get close enough, their intense gravitational pull distorts their accretion disks, warping the streams of gas and dust that fuel their immense energy output. Some simulations predict that right before merging, a double quasar system could unleash a final burst of radiation so powerful that it briefly outshines every other object in its galaxy. This final flash could be one of the brightest events in the universe, a last gasp before the two black holes spiral into one. But here's where things take an even stranger turn. Some models suggest that in the last moments before a merger, the combined energy of two black holes could be so great that it distorts spacetime in unexpected ways. Some researchers have proposed that under the right conditions, the energy from a merging quasar pair could briefly create a phenomenon known as a spacetime recoil, where the newly formed black hole gets kicked away at incredible speeds. In extreme cases, this could eject the resulting black hole completely out of its host galaxy, sending it speeding through the universe as a rogue black hole. If true, this means that some of the biggest black holes in the universe might not even be inside galaxies. They could be drifting alone in the void, undetectable except for the occasional flash of radiation they emit when consuming stray matter. The study of double quasars is still in its early stages, but the technology to uncover their secrets is advancing rapidly. With upcoming telescopes like the Extremely Large Telescope, ELT, and space missions like the Nancy Grace Roman Space Telescope, astronomers will soon have the ability to peer deeper into the universe than ever before. These advanced observatories will allow scientists to find more double quasars, analyze their behavior in unprecedented detail, and maybe even catch one in the act of merging. So what does all this mean for our understanding of the universe? Double quasars aren't just rare cosmic oddities. They are keys to some of the most profound questions in astrophysics. They provide insights into how galaxies grow and evolve, how black holes interact, and how the universe itself is structured. They allow us to test Einstein's theories on the largest scales, probe the nature of dark matter, and even refine our models of cosmic expansion. Each new discovery brings us closer to understanding the grand mechanisms driving the cosmos. And yet, for every answer we find, more mysteries emerge. Could there be triple or even quadruple quasars hidden in the universe? What if the mergers of supermassive black holes create exotic new states of matter or unknown forms of radiation? Could studying double quasars one day help us unlock the secrets of quantum gravity, the long-sought link between general relativity and the strange world of quantum mechanics? The questions are endless, and the search has only just begun. The search for double quasars is not just about identifying these rare objects, it's about understanding the fundamental forces that shape our universe. Every new discovery leads to new puzzles, forcing scientists to rethink existing models of black hole evolution, galaxy formation, and even the nature of spacetime itself. But beyond the physics, double quasars also provide something even more profound, a glimpse into the distant past, allowing us to see cosmic events that happened billions of years ago. One of the most astonishing aspects of studying quasars is that they act as time machines. Because they are so far away, the light we observe from them today has been traveling for billions of years. This means that when we look at a double quasar, we're not seeing it as it is now, we're seeing it as it was when the universe was much younger. In some cases, we might be witnessing a moment from just a few 100 million years after the Big Bang, a time when galaxies were still forming and the first supermassive black holes were coming to life. But this also raises a fascinating question: how did these massive black holes form so early in the universe? According to our current understanding of black hole growth, supermassive black holes take billions of years to accumulate enough mass to reach quasar status. Yet, astronomers have found quasars that existed less than a billion years after the Big Bang. This suggests that black holes might have formed much faster than we previously thought, or that an entirely new mechanism is at play. One possible explanation is that some of the first black holes in the universe didn't form from dying stars, as most black holes do today. Instead, they might have formed directly from the collapse of enormous clouds of gas, skipping the star phase entirely. These direct collapsed black holes could have reached supermassive sizes much more quickly than their stellar-born counterparts, explaining how quasars appeared so early in the universe. If this theory is correct, then studying double quasars from the early universe could provide crucial evidence for how these primordial giants formed. Another theory suggests that some of the earliest galaxies were much more efficient at feeding their central black holes. Normally, black holes grow by pulling in surrounding gas and dust, a process that can take millions or even billions of years. But in the chaotic conditions of the early universe, galaxies were colliding and merging at an accelerated rate. These violent interactions could have funneled enormous amounts of material into black holes, allowing them to reach quasar status much faster than previously believed. This idea ties directly into the study of double quasars. If quasars form most frequently in merging galaxies, then finding more double quasars from the early universe would provide strong evidence that galaxy collisions played a major role in supermassive black hole growth. It would also help us understand whether these early mergers were different from the galaxy interactions we see today. But there's another mystery lurking in the shadows, one that challenges our understanding of dark matter itself. When astronomers study the motion of galaxies, they find that the visible matter alone isn't enough to explain their movement. Something unseen, something massive, is exerting gravitational influence on these galaxies. This invisible substance is what we call dark matter, and although it makes up most of the universe's mass, no one knows exactly what it is. Quasars provide a unique way to study dark matter because their powerful light can act as a natural probe of the space around them. When light from a quasar passes through a region of space filled with dark matter, the gravity of that dark matter can bend and magnify the quasar's light, an effect known as gravitational lensing. In some cases, this lensing effect can even create the illusion of multiple quasars where only one actually exists. This is where things get really strange. Sometimes, what appears to be a double quasar isn't actually two black holes. It's a single quasar whose light has been split and duplicated by the gravity of an unseen object in between. This means that astronomers have to be extremely careful when identifying double quasars, because some of them might not be binaries at all, but instead be optical illusions caused by gravitational lensing. However, this phenomenon also presents an incredible opportunity. If we can study these lensing effects in detail, we can map the distribution of dark matter in the universe with unprecedented accuracy. In other words, quasars, whether single or double, might hold the key to unlocking one of the biggest mysteries in modern physics. And yet, there's still more to uncover. Some scientists believe that the study of double quasars could even help us test alternative theories of gravity. Einstein's general relativity has passed every test we've thrown at it, but there are still unresolved questions, especially when it comes to the extreme environments near black holes. By studying how double quasars interact and move over time, astronomers might be able to detect subtle deviations from Einstein's predictions, providing hints of new physics beyond our current understanding. The implications of this are staggering. If double quasars reveal even the slightest anomaly in the way gravity behaves, it could point toward new fundamental forces, undiscovered particles, or even entirely new dimensions of reality. Some physicists speculate that these observations could provide indirect evidence for quantum gravity, the long-sought theory that unifies Einstein's relativity with the bizarre world of quantum mechanics. But perhaps the biggest unanswered question is what happens after a double quasar finally merges into a single, even more massive black hole. We know that when two black holes collide, they release an enormous burst of gravitational waves. But if these black holes are also quasars, actively devouring material, the final moments of their merger could create some of the most energetic explosions in the universe. Some simulations suggest that a merging double quasar could produce an outburst so powerful that it briefly outshines an entire galaxy. This could create what's known as a quasar tsunami, where massive waves of radiation and high-energy particles sweep across space, altering the evolution of nearby galaxies. If such an event were to occur in our own cosmic neighborhood, it could have profound effects on star formation, planetary atmospheres, and even the future habitability of certain regions of space. This raises a chilling thought. What if a merging quasar could release enough energy to disrupt entire galactic civilizations? If advanced extraterrestrial life exists, could they have detected and even predicted these cosmic cataclysms? And if so, what steps would they take to survive? The more we learn about double quasars, the more we realize that we're only scratching the surface of their true nature. These objects are not just relics of the past. They are active, evolving powerhouses that continue to shape the universe in ways we are only beginning to understand. As technology advances and our ability to study these distant objects improves, we may soon uncover answers to some of the most profound questions in physics, cosmology, and the origins of the universe itself. But as with all great mysteries, every discovery leads to new unknowns. Could there be entire clusters of merging quasars hidden in the distant universe? Do double quasars behave differently in regions of extreme dark matter concentration? And could studying these objects one day reveal something so fundamental that it rewrites everything we thought we knew about space and time? Only time, and deeper exploration, will tell. The study of double quasars is not just about finding pairs of supermassive black holes. It is about uncovering the hidden dynamics of the cosmos. Every double quasar discovered provides another data point in our understanding of galaxy mergers, black hole growth, and even the fundamental nature of spacetime itself. But with every answer we uncover, new questions emerge, questions that push the limits of what we think is possible. One of the most intriguing aspects of double quasars is how they influence their surroundings. We already know that single quasars release immense amounts of energy, sometimes shaping entire galaxies by blasting out radiation and powerful winds that can either trigger or suppress star formation. But when two quasars exist in close proximity, the effects could be even more extreme. Some researchers speculate that double quasars could create enormous shockwaves that ripple through the gas clouds of their host galaxies, disrupting star formation on a massive scale. Others suggest that their combined gravitational forces could significantly warp spacetime, producing effects that we have yet to fully understand. This leads to an even deeper question: what happens when two active quasars eventually merge into one? Unlike regular black hole mergers, which occur in relative silence apart from their gravitational wave signals, a quasar merger could be one of the most dramatic events in the universe. As the two black holes spiral inward, they drag along vast amounts of surrounding gas and dust, creating an intense whirlpool of radiation that could temporarily outshine entire galaxies. Some researchers believe that these merging quasars might also generate bursts of high-energy particles that could travel across intergalactic space, potentially impacting planets, including our own, millions or even billions of years later. These quasar mergers may also be key to understanding the mysterious origins of the largest black holes in the universe. There are some black holes that are so massive, tens of billions of times the mass of the Sun, that their origins defy conventional explanations. One possibility is that these giants formed through repeated quasar mergers over billions of years. If so, then double quasars could be the missing link in explaining how some of the largest structures in the universe came to be. But while double quasars help us understand the past, they may also provide insights into the future of our own galaxy. The Milky Way is currently on a collision course with the Andromeda Galaxy, a massive spiral galaxy located about 2.5 million light-years away. In about 4 billion years, the two galaxies will merge, creating a new, larger galaxy sometimes referred to as Milkomeda. Scientists predict that during this process, the supermassive black holes at the center of both galaxies will eventually come together, potentially forming a double quasar before merging into an even more massive black hole. This means that studying distant double quasars is not just an exercise in cosmic archaeology. It's a preview of what may one day happen in our own galactic neighborhood. However, studying these double quasars is far from easy. Because they are so far away, many of them appear as tiny points of light, indistinguishable from single quasars unless observed with incredibly precise instruments. One of the biggest challenges for astronomers is distinguishing a true double quasar from other objects that might mimic its appearance, such as gravitationally lensed quasars. These occur when a single quasar's light is bent and split by a massive intervening object, making it appear as though there are two or more quasars where only one actually exists. To separate true double quasars from these illusions, scientists use a combination of techniques. One method is analyzing the spectral signatures of each quasar. If they show subtle differences in their composition or movement, it's likely that they are distinct objects rather than just multiple images of the same one. Another approach involves looking at their surrounding galaxies in detail. If two quasars are part of the same merging galaxy, it strongly suggests that they are indeed a genuine pair rather than a mirage created by gravitational lensing. In recent years, new technology has dramatically improved our ability to detect and study double quasars. Instruments like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, are providing unprecedented levels of detail, allowing astronomers to peer deeper into space than ever before. These telescopes are not only finding more double quasars but also revealing surprising details about their structure, their interactions, and their role in shaping the evolution of the universe. One of the most exciting discoveries has been the realization that some double quasars are much closer to merging than previously thought. In some cases, the two black holes may be just a few light-years apart, an incredibly small distance on a cosmic scale. At this range, the effects of their gravitational interactions become extreme, warping the spacetime around them in ways that could provide new tests for Einstein's theory of relativity. Some researchers believe that studying these near-merger quasars could even reveal hints of new physics beyond Einstein's equations, potentially shedding light on the long-sought connection between general relativity and quantum mechanics. But perhaps the most tantalizing possibility is that double quasars could provide a new way to search for signs of extraterrestrial intelligence. If an advanced civilization were to observe a double quasar in its final stages of merging, they might recognize it as a significant cosmic event, one that could have dramatic effects on surrounding star systems. Some scientists speculate that extraterrestrial civilizations might try to harness or study the energy released by such mergers, potentially leaving behind detectable signs of their activity. This raises an even more mind-bending question: could an intelligent species ever manipulate a double quasar merger for their own purposes? While this might sound like pure science fiction, the idea of civilizations harnessing black holes for energy is not entirely far-fetched. Some physicists have proposed that highly advanced civilizations, so-called Type 3 civilizations on the Kardashev scale, might be able to extract energy from black holes using a technique known as the Penrose process. If such civilizations exist, could they have found ways to control or even engineer double quasar mergers? While there is currently no evidence to suggest that any civilization has done this, the idea remains an intriguing possibility, one that could become more relevant as we continue to study these cosmic behemoths in greater detail. Double quasars represent one of the most fascinating and mysterious phenomena in the universe. They challenge our understanding of black hole formation, galaxy evolution, and even the fundamental laws of physics. They provide a window into the early universe while also offering clues about the future of our own galaxy. And with each new discovery, they continue to remind us that the cosmos is far more complex and awe-inspiring than we ever imagined. But perhaps the greatest mystery of all is what we have yet to discover. As technology advances and our ability to study these objects improves, what new secrets will double quasars reveal? Will they force us to rewrite our theories of gravity and dark matter? Will they help us understand the origins of the most massive black holes in existence? Or will they lead us to something even more profound, something that changes our understanding of the universe itself? Only time will tell. But one thing is certain: the mysteries of double quasars are far from solved, and the deeper we look, the more questions we will find. The study of double quasars is a journey into the unknown, a pursuit that constantly challenges our understanding of the universe. While we have uncovered many details about their formation, evolution, and impact on galaxies, there is still so much we do not know. Every new observation brings new questions, pushing the boundaries of astrophysics and cosmology. One of the most significant questions surrounding double quasars is their role in shaping large-scale cosmic structures. The universe is not a random collection of galaxies floating in space. It is structured in vast networks of filaments, clusters, and voids, sometimes referred to as the cosmic web. This web-like arrangement of galaxies and matter is believed to have formed over billions of years due to the pull of gravity and the expansion of the universe. Double quasars, as markers of galaxy mergers and extreme gravitational interactions, may play a crucial role in shaping this structure. When two galaxies merge, their black holes and surrounding quasars do not simply collide in isolation. They disrupt their entire galactic environments, sending powerful waves of energy and radiation outward. These disturbances could influence nearby galaxies, altering their star formation rates, triggering new mergers, or even changing the movement of intergalactic gas. Some astronomers believe that clusters of double quasars might act as nodes within the cosmic web, guiding the large-scale flow of matter throughout the universe. But beyond their role in shaping cosmic structures, double quasars may also hold the key to understanding one of the biggest mysteries in physics: dark matter. This invisible substance, which makes up roughly 85% of the matter in the universe, cannot be seen directly. It can only be inferred through its gravitational effects on galaxies and light. Because double quasars are powerful sources of light and gravity, they provide a unique opportunity to study dark matter. One way this happens is through gravitational lensing. When light from a double quasar passes through a region of space containing dark matter, the dark matter's gravity bends and distorts the light, creating multiple images of the quasar. By carefully analyzing these distortions, scientists can map the distribution of dark matter in that region. This technique has already led to some surprising findings, revealing that dark matter may be clumpier and more complex than previously thought. Some researchers even speculate that unusual patterns in the lensing of double quasars could hint at new physics, perhaps even an entirely new type of matter or force that we have yet to discover. But dark matter is not the only mystery that double quasars could help solve. They may also provide insights into the nature of time itself. According to Einstein's theory of relativity, time is not an absolute constant. It can be stretched, compressed, and even slowed down in the presence of extreme gravitational forces. Because double quasars involve two supermassive black holes orbiting each other, they create some of the most intense gravitational fields in the universe. Some physicists believe that studying these interactions could reveal subtle effects on time, possibly offering new insights into the nature of spacetime and the origins of the universe. This leads to another mind-bending question. Could double quasars serve as natural laboratories for testing the concept of wormholes? Wormholes are hypothetical shortcuts through spacetime, connecting distant points in the universe. While no direct evidence for wormholes has been found, some scientists speculate that extreme gravitational interactions, such as those occurring in double quasars, could create conditions similar to what a wormhole might require. If a double quasar were found to exhibit unusual gravitational signatures or unexplained distortions in its light, it could hint at the presence of a hidden structure within spacetime itself. And then there's the question of what happens after a double quasar merger. While we know that two black holes will eventually collide and merge into a single, more massive black hole, the exact details of this process remain mysterious. Some simulations suggest that the final moments of a merger could produce an enormous burst of energy, possibly detectable as a unique signal in gravitational waves. Others predict that the newly formed black hole might be kicked out of its galaxy entirely due to an imbalance in the energy released, sending it hurtling through intergalactic space at incredible speeds. If such a scenario is real, it could mean that there are rogue supermassive black holes wandering through the universe, remnants of past double quasar mergers. As our telescopes become more powerful, we are beginning to see hints of these extraordinary events. Some astronomers believe they have already identified black holes in unusual locations, far from any galaxy center, suggesting that they may have been ejected in past mergers. If confirmed, this would be one of the most dramatic discoveries in astrophysics, proving that even the heaviest objects in the universe are not always bound to their host galaxies. But perhaps the biggest unanswered question is whether double quasars exist in even more extreme configurations. We have found pairs of quasars, but what about triples or quadruples? Could there be entire clusters of quasars orbiting each other in some distant corner of the universe? While such systems would be incredibly rare, they are not impossible. Some simulations suggest that in the densest regions of the cosmos, multiple galaxies could collide at once, forming chaotic, multi-quasar systems unlike anything we have ever seen. If such systems exist, they could push the limits of our understanding of black hole physics to new extremes. They might generate gravitational waves of unprecedented strength, potentially detectable by future space-based observatories. They could create enormous bursts of energy capable of reshaping entire galaxies. And they might even provide clues about the earliest moments of the universe, when the first black holes were forming and merging in rapid succession. With every discovery, the mystery of double quasars deepens. We now know they are more common than we once thought, that they influence galaxy evolution, that they provide unique insights into dark matter, and that they may hold clues about the very fabric of spacetime. But with every answer we uncover, we find even more questions. What happens when the largest double quasars merge? Could these events be responsible for the most massive black holes in the universe? Do they play a role in the unexplained acceleration of the universe's expansion? Could they help us detect hidden dimensions or unknown forces of nature? We are only beginning to scratch the surface of what double quasars can teach us. But one thing is certain: the more we look, the more we realize that the universe is far more complex, chaotic, and awe-inspiring than we ever imagined. And as new telescopes come online, new observations are made, and new theories emerge, the mysteries of double quasars will only continue to grow. The mystery of double quasars is not just about what we can see, it's also about what we can't see. The forces at play within these systems stretch the limits of our current understanding of physics. Every discovery leads to a cascade of new questions, pushing us to rethink our models of the universe. One of the most perplexing aspects of double quasars is how they evolve over time. We know that these objects are tied to galaxy mergers, but we don't yet fully understand how their interactions change over millions or even billions of years. For instance, when two quasars orbit each other, their gravitational influence distorts the space around them. This distortion affects everything nearby, including stars, gas clouds, and even dark matter. Scientists suspect that these gravitational interactions may lead to chaotic effects within their host galaxies. Some simulations suggest that a double quasar system can trigger a gravitational slingshot effect, in which stars are violently ejected from their galaxies at speeds approaching a significant fraction of the speed of light. These runaway stars could be scattered across intergalactic space, traveling alone through the void for billions of years. But what happens to the galaxies themselves? One hypothesis is that double quasars might be responsible for dead galaxies, galaxies that no longer form new stars. The intense radiation and winds from two supermassive black holes could be enough to blow away the gas needed for star formation. If this theory is correct, then the existence of double quasars could explain why some galaxies appear to be barren husks, stripped of the ability to create new stars. This would suggest that double quasars are not just passive objects, they may be actively shaping the life cycle of entire galaxies. And yet, some double quasars appear to be anomalies. Astronomers have found systems that don't quite fit the expected model, where the quasars seem to be moving in unexpected ways or producing light signatures that don't match our current understanding. Some scientists suspect that these anomalies might be due to interactions with exotic forms of matter, perhaps even dark energy, the mysterious force driving the expansion of the universe. Others propose that these strange behaviors could be linked to hidden black hole physics, processes that we haven't yet discovered. Another mind-boggling idea is that some double quasars might not be what they seem. While most are thought to be the result of galaxy mergers, there is a possibility that some could be evidence of something far more unusual: primordial black holes. These hypothetical objects are believed to have formed in the earliest moments of the universe, long before the first stars and galaxies. If primordial black holes exist, they could have remained hidden for billions of years, only becoming visible when they capture and consume matter. Could some double quasars actually be primordial black holes that have found themselves in close proximity by chance? If so, it would challenge much of what we believe about the formation of black holes and the evolution of the cosmos. Even more fascinating is the possibility that double quasars could provide a testing ground for one of the biggest unanswered questions in physics: the nature of gravity itself. Einstein's theory of general relativity has been incredibly successful in explaining the behavior of massive objects, but there are signs that it may not be the full story. Some researchers believe that extreme gravitational environments, like those found in double quasar systems, might reveal deviations from general relativity, small inconsistencies that could point to a deeper, more fundamental theory of gravity. If such deviations were found, they could revolutionize our understanding of the universe, potentially leading to the discovery of new fundamental forces or even evidence for extra dimensions. And then there is the question of cosmic time. Could double quasars be acting as natural timekeepers for the universe? Because the light from these objects has traveled for billions of years to reach us, they provide a window into the past. By comparing observations of double quasars at different distances, scientists might be able to detect subtle changes in the fabric of spacetime itself. Some physicists speculate that this could help us test whether the fundamental constants of nature, such as the speed of light or the strength of gravity, have remained the same throughout cosmic history. If any variation is found, it could mean that the laws of physics themselves are not as unchanging as we once thought. But perhaps the most astonishing possibility is that double quasars could hold the key to understanding the ultimate fate of the universe. Some cosmologists believe that the universe will end in a big freeze, where all the stars burn out and the cosmos becomes a cold, dark void. Others suggest a big rip, in which dark energy tears everything apart. Still, others propose a big bounce, where the universe collapses and then expands again in an endless cycle. Could double quasars provide evidence for one of these scenarios? Some researchers think they might, as the energy and gravitational waves they produce could reveal how the fundamental forces of the universe are evolving over time. The mystery of double quasars is far from solved. They challenge our understanding of black holes, galaxy formation, dark matter, dark energy, and even the fundamental laws of physics. Every new discovery raises more questions than it answers, and with each breakthrough, the universe seems to become even stranger and more complex. But that's what makes the study of double quasars so exciting. They are not just distant celestial objects, they are clues, scattered across the cosmos, waiting to be pieced together. And as our technology improves and our understanding deepens, we may one day unlock the true secrets of these enigmatic cosmic beacons. Until then, double quasars remain one of the greatest unsolved mysteries of space, a reminder that the universe is still full of surprises. The study of double quasars is not just about understanding distant celestial objects, it's about uncovering fundamental truths about the cosmos itself. Every piece of data gathered from these extraordinary systems has the potential to reshape what we know about black holes, gravity, and the very fabric of spacetime. But as with any great mystery, the more we learn, the more questions arise. One of the most intriguing aspects of double quasars is their role in the cosmic web, the vast structure of the universe made up of filaments of galaxies and dark matter. Some scientists suspect that double quasars may be more common in regions where galaxies are densely packed, providing clues about how matter is distributed on the largest scales. If this is true, then studying double quasars could help us map out the hidden skeleton of the universe, revealing how dark matter influences the formation and evolution of galaxies. But there's another possibility that is even more mind-bending. Could double quasars be linked to cosmic strings, hypothetical defects in spacetime that may have formed in the early universe? Some theoretical models suggest that if cosmic strings exist, they could act as gravitational lenses, bending and magnifying the light from distant objects. In rare cases, this could create the illusion of a double quasar, two images of the same object, separated by the influence of an invisible cosmic string. If such a discovery were made, it would be one of the most profound findings in modern physics, providing direct evidence for the exotic phenomena predicted by string theory. And then there's the mystery of their variability. Astronomers have noticed that some double quasars exhibit unexpected changes in brightness, sometimes dimming or flaring up in ways that don't match standard models. What could be causing this? One possibility is that these quasars are interacting with vast clouds of gas and dust, which momentarily obscure their light. Another is that unseen black holes are passing in front of them, acting as gravitational lenses and briefly magnifying their brightness. But there is also a more radical idea, that some double quasars might be connected by quantum entanglement. While this idea is purely speculative, it raises an astonishing question. Could quantum mechanics be playing a role on cosmic scales, linking two massive black holes across vast distances in a way that defies our current understanding of physics? And then, there is the question of time travel. If double quasars exist in warped regions of spacetime, could they act as natural laboratories for testing the nature of time itself? Some physicists have proposed that under extreme gravitational conditions, time could behave in unexpected ways. Could double quasars serve as evidence that time is not as linear as we perceive it? Could they be windows into the distant past, or even portals to alternate timelines? These ideas remain speculative, but as our technology advances, we may find new ways to test such mind-boggling theories. Even more perplexing is the question of whether double quasars could harbor exotic forms of matter. Some theories suggest that within the extreme environments of these systems, particles could behave in ways never before seen. Could the intense energy of a double quasar trigger the formation of strange matter, a hypothetical form of matter that could be even more stable than ordinary atomic nuclei? If so, this could have profound implications for our understanding of particle physics and even the ultimate fate of the universe. And then, there's the possibility that double quasars might not just be rare cosmic accidents, but rather an essential part of the cosmic cycle. If they are linked to galaxy mergers, and galaxy mergers drive cosmic evolution, then double quasars might be one of the key forces shaping the universe as we see it today. Their radiation, their gravitational waves, and their sheer power may be part of a larger cosmic engine, continuously reshaping the universe. So, what happens when two quasars finally collide? This is one of the most dramatic and violent events that could ever occur in the universe. As their black holes spiral toward each other, they release enormous amounts of energy in the form of gravitational waves, rippling across the cosmos. When they finally merge, they create an even more massive black hole, unleashing one last burst of energy before settling into a state of relative calm. But could there be more to the story? Some scientists speculate that these mergers might produce effects we can't yet predict, perhaps even creating new kinds of particles or altering the structure of space-time itself. The deeper we look into the mystery of double quasars, the more we realize that they are not just distant beacons of light. They are cosmic laboratories, natural experiments playing out on a scale beyond human comprehension. They may hold the answers to some of the greatest questions in science, from the nature of gravity to the fate of the universe itself. And yet, despite all we have learned, double quasars remain one of the greatest unsolved mysteries of space. They challenge everything we think we know, forcing us to confront the limits of our understanding. But that is what makes them so exciting. They remind us that the universe is still full of surprises, still full of the unknown. The mystery of double quasars goes beyond just what we can observe. They force us to ask deeper questions about the structure of reality itself. Could they be windows into hidden dimensions? Could their existence hint at new physics that we haven't even begun to comprehend? Some scientists speculate that the extreme gravitational conditions surrounding double quasars might allow us to test theories of quantum gravity, the long-sought-after unification of Einstein's general relativity and quantum mechanics. One of the strangest ideas in modern physics is that the fabric of spacetime itself might be granular at the smallest scales, composed of tiny, indivisible units, much like pixels on a screen. If this is true, then the high-energy environments of double quasars could reveal subtle distortions in the way light travels, potentially exposing the hidden structure of reality. But detecting such effects requires instruments far beyond what we currently have. Still, the possibility remains. Could double quasars be hinting at an underlying order to the cosmos, a deeper reality that we are only just beginning to glimpse? And what about their role in shaping the cosmic landscape? Some astronomers believe that double quasars could be responsible for some of the most dramatic transformations in the universe. As they interact with their host galaxies, they unleash winds powerful enough to strip entire regions of gas, shutting down star formation and altering the fate of entire star systems. Could double quasars be one of the main reasons why some galaxies appear dead, devoid of new stars? If so, then their influence extends far beyond their own immediate surroundings. But not all galaxies with double quasars are lifeless. Some seem to thrive despite, or perhaps because of, the presence of these powerful objects. In certain cases, the energy from double quasars might trigger bursts of star formation, igniting entire regions of space with new stellar nurseries. This paradoxical effect, where quasars both destroy and create, is yet another example of how little we truly understand about their role in the cosmos. And then there's the ultimate question: how many double quasars are out there? Right now, we've only identified a handful, but given the vastness of the universe, there could be countless more waiting to be discovered. Some may be so far away that their light has yet to reach us. Others may be hidden by thick clouds of dust, making them invisible to our current telescopes. What if some are even closer than we think, lurking in the depths of space, unnoticed? There is also the possibility that some double quasars might be illusions, trickery caused by gravitational lensing. In these cases, light from a single quasar is bent around a massive object, creating the appearance of two separate sources. Distinguishing between true double quasars and these optical illusions is one of the biggest challenges astronomers face. If we misinterpret our data, we might be drastically overestimating, or underestimating, the true number of double quasars in the universe. And yet, even with all these uncertainties, one thing is clear: double quasars are among the most extreme and fascinating objects in existence. They are cosmic laboratories where we can test our most ambitious ideas about black holes, gravity, and even the nature of time itself. They are reminders that the universe is far stranger and more complex than we ever imagined. As technology advances, new telescopes and space observatories will allow us to peer even deeper into the cosmos, revealing more double quasars and shedding light on their secrets. Perhaps in the coming decades, we will finally understand how they form, how they evolve, and what they can teach us about the grand story of the universe. But until then, they remain one of space's greatest unsolved mysteries, enigmatic, powerful, and awe-inspiring. The deeper we delve into the mystery of double quasars, the more we realize just how little we truly understand about them. These objects challenge our understanding of space, time, and the very nature of reality itself. The extreme conditions surrounding double quasars, intense gravitational forces, high-energy radiation, and the sheer magnitude of power they unleash, make them some of the most perplexing and awe-inspiring phenomena in the universe. But what if we are still missing something? What if there are aspects of these cosmic giants that we have yet to even consider? For instance, the question of how double quasars form is still not fully settled. The prevailing theory suggests that they arise from galaxy mergers, where two supermassive black holes from separate galaxies find themselves locked in a gravitational dance. Over millions of years, they spiral closer together, feeding off the surrounding matter and creating twin quasars in the process. But is this the only possible explanation? Some astronomers have proposed alternative scenarios, such as the idea that double quasars could form in more exotic environments, perhaps even in regions of space where dark matter is unusually dense. Could there be hidden mechanisms at play, processes we haven't yet identified that contribute to the birth of these incredible objects? And then there's the question of what happens when two quasars finally merge. The energy released in such an event would be beyond anything we can currently comprehend. When two supermassive black holes collide, they send ripples through the very fabric of space-time, generating gravitational waves that can travel across the universe. These waves were first directly detected by the LIGO Observatory in 2015, providing evidence for Einstein's general relativity in a way that had never been seen before. But what about when two active quasars, each one radiating with the power of trillions of stars, collide and merge. The sheer amount of energy unleashed could be on a scale that defies our current models, producing effects that go far beyond anything we have observed. Could such an event create new kinds of particles? Could it trigger exotic physics that only occur under these extreme conditions? One of the biggest unsolved mysteries surrounding double quasars is their variability. Unlike ordinary stars, which tend to shine with a relatively steady brightness, quasars can change in intensity, sometimes dramatically. But when two quasars are locked together in a gravitational embrace, their variability becomes even more unpredictable. Some double quasars have been observed to flicker in strange, seemingly random ways, leading astronomers to wonder if some unknown force is at play. One theory suggests that hidden structures within the accretion disk surrounding the black holes could be responsible, momentarily blocking or amplifying the light we see. Another possibility is that interactions between the two quasars themselves create feedback loops of energy, causing fluctuations that we do not yet fully understand. But what if the explanation is even stranger? Some physicists have speculated that extreme environments like double quasars could serve as natural testing grounds for quantum mechanics on a cosmic scale. In the realm of quantum physics, particles can become entangled, meaning that changes to one particle instantaneously affect another, no matter how far apart they are. While quantum entanglement has been observed in laboratory experiments on Earth, could something similar be happening on a much larger scale with double quasars? Could their light be connected in ways we don't yet understand, hinting at a deeper, hidden order to the universe? Another puzzling aspect of double quasars is their alignment with large-scale cosmic structures. Some studies have suggested that quasars tend to be arranged along vast, filament-like structures in the universe, forming a kind of cosmic web. But why would quasars, objects powered by individual black holes, follow such an orderly pattern on a scale spanning billions of light-years? One hypothesis is that this alignment is the result of ancient cosmic forces, imprinted on the universe during its earliest moments. If so, then double quasars might not just be random phenomena but rather key players in the grand design of the cosmos. And then there is the matter of dark matter. While dark matter itself does not emit light, it interacts with ordinary matter through gravity, shaping the structure of galaxies and clusters. Some scientists believe that double quasars could be useful tools for studying dark matter, as their intense gravity allows us to see how light bends around them. If a double quasar is surrounded by a dense halo of dark matter, it could distort the space around it in ways that we might be able to detect. Could double quasars be the key to finally unlocking the secrets of dark matter, one of the biggest unsolved mysteries in modern physics? The nature of time itself also comes into question when studying double quasars. Under the influence of extreme gravity, time slows down, a phenomenon predicted by Einstein's theory of general relativity. But how does this effect play out when two supermassive black holes are in motion relative to each other? Some theorists have suggested that time near a double quasar could behave in bizarre ways, possibly even creating temporal distortions. Could this mean that double quasars act as natural time machines, allowing us to peer into different eras of cosmic history? If so, then the study of these objects could provide new insights into the nature of time itself. And what if some double quasars are not what they seem? While many double quasars are believed to be genuine pairs of supermassive black holes, some could be illusions created by gravitational lensing. In these cases, the light from a single quasar is bent around a massive object, such as a galaxy or even a black hole, creating the appearance of two separate sources. Distinguishing between true double quasars and lensing effects is crucial for understanding their true population in the universe. But what if some cases of gravitational lensing are more exotic than we currently realize? Could there be unknown forms of matter, perhaps even primordial black holes or exotic particles, causing light to bend in unexpected ways? The more we study double quasars, the more questions arise. They challenge our understanding of black holes, galaxy formation, dark matter, and even the fundamental nature of reality. Each new discovery leads to more mysteries, making them one of the most fascinating and perplexing topics in modern astrophysics. With new telescopes and advanced observational techniques, we are on the verge of uncovering even more about these enigmatic objects. But for now, double quasars remain one of the greatest unsolved mysteries of space, a cosmic enigma waiting to be unraveled. As we continue exploring the mystery of double quasars, we begin to realize that their significance goes beyond their immediate existence. They are not just individual objects floating in the vastness of space. They are pieces of a much larger cosmic puzzle. Every double quasar we discover brings us closer to understanding the underlying mechanisms that shape the universe itself. The more we study them, the more we realize how interconnected everything is, from the formation of galaxies to the structure of the cosmic web, to the very forces that govern space and time. But the truth is, we are only scratching the surface. There is still so much we do not know. One of the greatest questions about double quasars is whether they are common or rare. Given the vastness of the universe, it seems logical that there should be millions, perhaps even billions, of them out there. And yet, we have only detected a handful. Why is that? Are they simply too far away for us to see? Are they hidden behind clouds of intergalactic dust, waiting to be revealed by future telescopes? Or could it be that double quasars are a brief, fleeting phase in the life cycle of galaxies, appearing only under very specific and rare conditions? If double quasars are indeed a short-lived phenomenon, then we are incredibly fortunate to have observed any at all. It could mean that we are witnessing an event that occurs only once every few billion years in a given galaxy. If that is the case, then double quasars may be a critical but transient stage in the evolution of galaxies, appearing just before the final merger of two supermassive black holes. If we could observe this process in real time, if we could watch as two quasars spiral closer together and eventually merge, it would be one of the most groundbreaking discoveries in astrophysics. But given the immense timescales involved, such an event is unlikely to be observed within a human lifetime. Instead, we must rely on indirect observations, piecing together the story from different double quasars at various stages of their evolution. But what if some double quasars never merge? What if, under certain conditions, two supermassive black holes can remain locked in an eternal gravitational struggle, circling each other endlessly? This raises an even more mind-bending possibility. Could there be double quasars that have been orbiting each other since the early universe, surviving for billions of years without ever fully merging? If such objects exist, they could provide crucial clues about the history of the cosmos, offering a direct link to the conditions that prevailed in the first few 100 million years after the Big Bang. And then, of course, there is the question of what happens to the space around double quasars. The immense gravitational forces they generate can warp and bend the fabric of spacetime itself, creating bizarre distortions that challenge our understanding of physics. Some scientists have even speculated that the intense warping of spacetime near a double quasar could create temporary wormholes, shortcuts through space that might, under the right conditions, allow for faster-than-light travel. While this remains purely speculative, it raises the fascinating possibility that double quasars could be linked to some of the most exotic and unexplored aspects of physics. There is also the possibility that double quasars could help us understand the ultimate fate of the universe. The way they interact with their surroundings, the way they shape and influence the galaxies around them, could provide insights into how the cosmos as a whole evolves. Some theories suggest that as the universe expands, galaxies will eventually drift apart, and star formation will slow down until the cosmos becomes cold and dark. If double quasars play a role in regulating star formation, they could be one of the mechanisms that determine how quickly or slowly this process unfolds. But what if the opposite is true? What if, instead of signaling the slow death of the universe, double quasars are actually signs of renewal? Some scientists believe that the energy they release can trigger the birth of new stars, reigniting regions of space that might otherwise have remained lifeless. If this is the case, then double quasars are not just destructive forces but also agents of cosmic rebirth, playing a role in the eternal cycle of creation and destruction that defines the universe. And yet, for all we know about double quasars, there is still so much we do not understand. Their extreme brightness makes them difficult to study in detail, as their intense light can overwhelm even the most advanced telescopes. Their distances make them difficult to observe, with many existing at the very limits of what we can detect. Their nature as massive, chaotic objects means that their behavior is unpredictable, often defying our expectations. This is why the next generation of telescopes, such as the James Webb Space Telescope and the upcoming Extremely Large Telescope, are so crucial. These instruments will allow us to see double quasars with unprecedented clarity, revealing details we could never have imagined. With these new tools, we may finally be able to answer some of the biggest questions surrounding double quasars: how they form, how they evolve, and what role they play in shaping the universe. But even as we prepare to unlock these secrets, we must acknowledge that the universe will always hold mysteries beyond our comprehension. For every question we answer, a dozen more arise. For every discovery we make, new enigmas present themselves. And perhaps that is the true beauty of space, the fact that it will always remain, in some way, unknowable. Double quasars are a reminder of this, a testament to the infinite complexity of the cosmos. They are both a mystery and a promise, an invitation to keep looking, keep questioning, and keep pushing the boundaries of what we understand. As we continue to explore the universe, double quasars will remain one of the most fascinating and challenging puzzles of modern astrophysics. They remind us that, despite all our advances, we are still at the very beginning of our journey into the cosmos. And perhaps, in the end, the greatest mystery of all is not the universe itself, but our endless desire to understand it. The story of double quasars is far from over, and in many ways, we are only beginning to uncover their true significance. These cosmic powerhouses exist on such vast scales that even the best telescopes we have today are only giving us glimpses of their full nature. Every time we detect a new double quasar, it brings us one step closer to answering some of the biggest questions about the universe, but at the same time, it also deepens the mystery. Why do some galaxies seem to host double quasars while others do not? Are these objects truly as rare as they seem, or are we just looking in the wrong places? Could it be that we are missing entire populations of double quasars because they are hidden behind layers of cosmic dust or disguised in ways we do not yet understand? One of the key challenges in studying double quasars is the fact that they are often mistaken for single quasars. Because they are so far away, the two quasars in a pair can appear so close together that they blend into a single point of light when observed with less powerful instruments. It takes the most advanced telescopes, combined with detailed spectroscopic analysis, to separate the light of two quasars and confirm that they are indeed distinct objects rather than a single quasar with an unusual structure. This means that there could be many more double quasars out there, hidden in plain sight, waiting to be discovered. This problem is made even more complex by the fact that some double quasars appear to be gravitationally lensed. When the light from a distant double quasar passes through a massive galaxy or cluster of galaxies on its way to Earth, the intense gravitational field of the intervening object can bend and distort the light, creating multiple images of the same quasar. In some cases, this lensing effect can make it look as though there are 4 or more quasars in the same location, when in reality, there are only 2. This makes identifying true double quasars an incredibly difficult task, requiring astronomers to carefully analyze each observation to determine whether they are looking at a real double quasar or just an illusion created by gravitational lensing. But why do double quasars matter so much? What makes them more significant than single quasars or other high-energy objects in space? The answer lies in their ability to provide unique insights into some of the most fundamental processes shaping the universe. For one, double quasars are key to understanding the dynamics of galaxy mergers. When two massive galaxies collide, their supermassive black holes do not immediately merge. Instead, they go through a long and complex process of interaction, gradually spiraling closer together over millions or even billions of years. During this time, the intense gravitational forces between the two black holes can lead to the formation of a double quasar, as material falling into each black hole is heated and accelerated to extreme speeds, producing the brilliant light that makes quasars so distinctive. By studying double quasars, scientists can learn how supermassive black holes interact with each other and with their surrounding galaxies. They can observe how the energy released by the quasars affects the gas and stars around them, potentially triggering new waves of star formation or, in some cases, blowing away the material needed for future star formation. This, in turn, helps us understand the role that quasars play in shaping the evolution of galaxies over cosmic time. Another major reason why double quasars are so important is their potential role in testing Einstein's theory of general relativity. According to this theory, when two supermassive black holes orbit each other, they should emit gravitational waves, ripples in the fabric of spacetime that spread outward at the speed of light. While we have already detected gravitational waves from the mergers of smaller black holes, the gravitational waves produced by merging supermassive black holes are on much longer wavelengths and have not yet been directly observed. Double quasars provide a unique opportunity to study these processes in action. Scientists are currently using radio telescopes to search for evidence of gravitational waves from double quasars by looking for tiny variations in the timing of signals from distant pulsars. If successful, this research could open up an entirely new way of studying the universe, allowing us to observe the mergers of supermassive black holes in real time and test our theories about how these objects influence the structure of space itself. But beyond their scientific significance, double quasars also raise deeper, more philosophical questions about the nature of the universe. The fact that these objects exist at all is a reminder of the incredible complexity of cosmic evolution. They challenge our assumptions about how galaxies form and grow, and they force us to confront the vast, almost unimaginable scales of time and space involved in these processes. Consider this: when we observe a double quasar, we are seeing it as it existed billions of years ago, long before the Earth even formed. The light from these objects has traveled across the universe for an unfathomable amount of time, crossing vast cosmic distances before finally reaching our telescopes. In many cases, the galaxies hosting these double quasars may no longer even exist in their original form. They may have long since merged into a single galaxy, their black holes having combined into one even larger supermassive black hole. Yet, for us, they are frozen in time, offering a glimpse into an ancient past that we can never directly witness. This raises an even more mind-bending possibility. Could some of the double quasars we see today actually be remnants of an earlier cosmic epoch, perhaps even relics from the very first galaxies that formed after the Big Bang? If so, studying them could provide us with a direct link to the earliest moments of the universe, helping us piece together the story of how the cosmos evolved from its chaotic, primordial state to the vast and structured universe we see today. At the same time, double quasars also hint at mysteries we have not yet even begun to unravel. For instance, could there be triple or even quadruple quasars, systems where multiple supermassive black holes are locked in a gravitational dance, each influencing the others in ways we cannot yet predict? Could some of these objects exist in strange, exotic states where the usual laws of physics begin to break down, revealing new aspects of reality we have never encountered before? And what about the role of dark matter and dark energy in shaping these systems? We know that most of the universe is made up of these mysterious, invisible forces, yet we still have almost no idea what they really are. Could double quasars offer clues about how dark matter influences the growth of galaxies and black holes? Could they provide hints about the nature of dark energy, the force that seems to be driving the accelerated expansion of the universe? These are the kinds of questions that make double quasars so fascinating. They are not just rare and beautiful cosmic objects, they are windows into some of the deepest mysteries of existence. They force us to confront the limits of our knowledge, to question our assumptions, and to push the boundaries of what we think is possible. And perhaps that is the most exciting thing of all. Because as long as there are mysteries like double quasars waiting to be uncovered, we will never run out of reasons to explore, to wonder, and to dream. The universe is vast, and we have barely begun to scratch the surface. But every new discovery brings us closer to understanding the incredible, interconnected web of forces that shape our reality. And in that pursuit, there is no end, only new questions, new challenges, and new wonders waiting to be revealed. Double quasars represent some of the most enigmatic structures in the universe, and as we continue to study them, the more profound their implications become. Their existence challenges our understanding of galaxy formation, black hole interactions, and even the very fabric of space and time. Each discovery of a double quasar is not just another data point. It is a window into a past that has long since faded from reality. And yet, through these brilliant celestial beacons, we are granted a glimpse into that ancient past, a glimpse that continues to reshape everything we know about the cosmos. One of the most striking aspects of double quasars is how they form in the first place. To have two active quasars in such close proximity, there must be an extreme and rare set of circumstances. A normal galaxy does not just produce two quasars at random. There has to be a history of dramatic events, typically a galaxy collision. When two massive galaxies, each hosting its own supermassive black hole, begin to merge, an intricate gravitational ballet unfolds over billions of years. These two black holes are initially separated by thousands of light years, but their immense gravity pulls them together over time. As they spiral closer, the environment around them becomes violently energetic. The gas and dust within the merging galaxies get funneled toward the two black holes, triggering intense accretion. This is when matter is drawn toward the black hole, forming a swirling disk that reaches temperatures of millions of degrees, emitting vast amounts of radiation. The light from these accretion disks is what makes quasars so incredibly bright, often outshining the combined light of an entire galaxy. But what happens next? This is where things become truly mysterious. The two black holes, each consuming vast amounts of energy, continue their dance, slowly moving closer due to the emission of gravitational waves. These ripples in spacetime, predicted by Einstein's general relativity, carry energy away from the system, allowing the two black holes to inch toward an eventual merger. However, we are yet to observe the final moments of such a merger directly. Scientists believe that when these titanic forces finally collide, the resulting burst of gravitational waves will be powerful enough to be detected across the universe. This is one of the reasons astronomers are so eager to find more double quasars. They provide crucial evidence of this merging process in action. By studying them, we can gain deeper insights into how often these events occur, how long they last, and what happens to the galaxies that host them. Understanding these processes is key to solving a much bigger mystery. How do the most massive black holes in the universe form? It is known that most galaxies, including our own Milky Way, contain supermassive black holes at their centers. But the exact process by which these behemoths grow to millions or even billions of times the mass of our Sun remains a topic of intense debate. One theory suggests that these giant black holes started as smaller, black holes, formed from the collapse of massive stars in the early universe. Over billions of years, they grew by consuming gas and merging with other black holes, eventually reaching their enormous sizes. If this is true, then double quasars might be the missing piece of the puzzle. They represent an intermediate stage in this growth process, showing us how black holes combine to form even larger ones. By examining the properties of double quasars, such as their separation, brightness, and surrounding environment, we can begin to reconstruct the sequence of events that leads to the creation of the largest black holes in existence. But there is another aspect of double quasars that makes them even more intriguing: their role as cosmic beacons that illuminate the dark corners of the universe. Because they are so bright, quasars can be seen from distances of billions of light years, meaning that when we observe them, we are looking far back into the past. Some of the double quasars we have detected today existed when the universe was only a fraction of its current age. They offer us a rare opportunity to study conditions in the early cosmos, revealing how the first galaxies evolved and how the first black holes came into being. In fact, some researchers believe that double quasars might help solve another long-standing mystery: the nature of dark matter. This invisible substance makes up most of the universe's mass, yet it does not emit, absorb, or reflect light, making it incredibly difficult to detect. However, dark matter does have gravitational effects, and it is thought to play a crucial role in the formation of galaxies. Some theories suggest that dark matter might influence the movement and interaction of supermassive black holes, potentially affecting the formation of double quasars. If this is true, then detailed studies of double quasars could provide indirect evidence of dark matter's role in shaping the universe. By measuring how these quasars move and interact, scientists could potentially detect subtle gravitational influences that hint at the presence of dark matter. This would be a groundbreaking discovery, bringing us one step closer to understanding one of the biggest unsolved mysteries in cosmology. But there is still another possibility, one that is even more mind-bending. Could double quasars be a sign of something even more exotic? Something that goes beyond our current understanding of physics? Some speculative theories suggest that if two black holes orbit each other in just the right way, they might produce strange and unexpected effects, such as distortions in time itself. Could it be that double quasars are not just massive black holes in the process of merging, but also natural laboratories for testing the very limits of physics? This idea is not as far-fetched as it might seem. In recent years, physicists have been searching for ways to unify general relativity, the theory that describes gravity on cosmic scales, with quantum mechanics, the theory that governs the behavior of particles on the smallest scales. These two theories are both incredibly successful, yet they are fundamentally incompatible with each other. Some scientists believe that extreme environments, such as those found around double quasars, could reveal clues about how these two theories might be reconciled. For instance, if gravitational waves from merging double quasars exhibit unexpected properties, such as variations in speed or intensity, it could suggest that our current understanding of spacetime is incomplete. Some researchers even speculate that these systems could produce exotic phenomena like quantum foam, where spacetime itself becomes turbulent and chaotic at microscopic scales. If such effects were detected, they would revolutionize physics, opening the door to entirely new theories about the nature of reality. And yet, despite all these possibilities, we are still only scratching the surface of what double quasars can teach us. Every new discovery raises more questions than it answers, fueling our desire to keep looking deeper into the universe. With the next generation of telescopes, such as the James Webb Space Telescope and future space-based gravitational wave detectors, we may soon uncover even more double quasars, perhaps in greater numbers than we ever imagined. What we do know is that these objects are far more than just rare astronomical curiosities. They are keys to unlocking some of the most profound secrets of existence. They challenge our understanding of cosmic evolution, test the limits of our physical theories, and offer glimpses into the earliest epochs of the universe. The more we study them, the more they remind us just how little we truly know about the cosmos, and how much there is still left to discover. And perhaps that is the greatest mystery of all. Because as long as double quasars exist, shining like distant lighthouses in the vast ocean of space, they will continue to beckon us forward, urging us to keep asking, to keep exploring, and to keep pushing the boundaries of human knowledge. Double quasars are not just fascinating because of their brightness or their extreme environments. They also act as natural experiments that test our most fundamental assumptions about the universe. They force us to question the way we understand gravity, space-time, and the very fabric of reality itself. The gravitational pull of these merging supermassive black holes is so intense that it warps the space around them, creating some of the most powerful gravitational lensing effects ever observed. This bending of light allows astronomers to study not just the quasars themselves but also the matter that lies between us and these distant objects. One of the most significant discoveries related to double quasars is their ability to reveal hidden structures in the cosmos. When light from a quasar passes through a massive galaxy or a cluster of galaxies on its way to Earth, the gravitational field of that intervening object bends and magnifies the light, creating multiple images of the same quasar. This phenomenon, known as gravitational lensing, has allowed astronomers to detect structures in space that would otherwise be invisible. Some of these structures include dark matter halos, massive, unseen regions of gravity that are thought to envelop galaxies and clusters. Gravitational lensing caused by double quasars also helps scientists test one of Einstein's most famous predictions, the bending of light by gravity. General relativity predicts that light traveling near a massive object will follow a curved path, and by measuring how much the light from a quasar is distorted, astronomers can test the accuracy of Einstein's equations on the largest cosmic scales. So far, every observation has confirmed that Einstein was right. But could double quasars one day reveal an exception, something that hints at new physics beyond general relativity? Another mystery surrounding double quasars is how they affect their surrounding galaxies. Supermassive black holes are not just passive objects that sit at the center of galaxies. They are powerful engines of change. When two quasars are active in the same galaxy, their combined energy output is so immense that it can disrupt star formation across vast distances. This process, known as quasar feedback, can push away or even completely blow out the gas needed to form new stars, effectively halting a galaxy's growth. Astronomers believe that this process plays a crucial role in shaping the evolution of galaxies. By studying double quasars, we can learn more about how galaxies grow, change, and sometimes even die. Some models suggest that the energy released during a quasar merger can create enormous shockwaves that travel through the galaxy, triggering bursts of star formation in some regions while shutting it down in others. Understanding this balance could be the key to solving the puzzle of why some galaxies continue forming stars for billions of years while others seem to stop abruptly. But there is yet another layer to this mystery, one that connects double quasars to the structure of the universe itself. Scientists have noticed that quasars are not randomly scattered across the cosmos. Instead, they appear to be arranged in vast, intricate patterns that hint at the underlying distribution of dark matter. Some researchers have suggested that double quasars might be more common in certain regions of the universe, particularly in areas where galaxies are more densely packed. If this is true, it could provide crucial evidence for how dark matter influences the formation of cosmic structures on the largest scales. Recent studies using advanced telescopes have even detected what appear to be triple or quadruple quasar systems, objects that could represent an even more extreme stage in this cosmic dance. If two merging galaxies can create a double quasar, what happens when 3 or 4 galaxies collide? Could such a system produce a chain reaction of black hole mergers, leading to the formation of some of the most massive black holes in existence? The discovery of these rare multiquasar systems suggests that the early universe may have been far more chaotic than previously thought. In the first billion years after the Big Bang, galaxies were still forming and merging at an incredible rate. During this time, it is possible that many of them contained multiple active quasars, creating some of the most extreme environments ever seen. But what about the future? Will we one day witness the final moments of a double quasar merger? The answer is complicated. Most of the double quasars we observe today are billions of light years away, meaning that we are seeing them as they were in the distant past. By the time their light reaches us, these systems may have already merged into single, even more powerful black holes. However, with the next generation of telescopes and gravitational wave detectors, we may finally be able to detect the ripples in spacetime caused by these cosmic collisions. The upcoming Laser Interferometer Space Antenna, LISA, set to launch in the 2030s, will be the first mission capable of detecting low-frequency gravitational waves from merging supermassive black holes. If double quasars are as common as some scientists suspect, LISA may pick up signals from these events on a regular basis, providing us with direct evidence of their final stages. This would mark a major turning point in astrophysics. For the first time, we would not just be observing the light from double quasars, we would be listening to the gravitational echoes of their collisions. These signals could tell us more about the nature of spacetime, the properties of black holes, and perhaps even the existence of extra dimensions or hidden forces beyond our current understanding. Even as we push the boundaries of our knowledge, double quasars continue to present new challenges. Some of the systems we have discovered defy explanation, exhibiting unusual behavior that does not fit our existing models. Some appear to change brightness unpredictably, while others show signs of interactions that cannot yet be fully explained. Could there be unknown physics at play? Or are we simply missing key details about how these objects evolve? One particularly strange case involved a double quasar that seemed to flicker in a way that suggested an unseen object was passing in front of it. Some astronomers speculated that this could be evidence of an invisible, rogue, black hole moving through space. If true, this would suggest that there may be many more wandering black holes in the universe than previously thought. These objects could be remnants of past galaxy collisions, roaming through the cosmos undetected, except when they briefly pass in front of a quasar and reveal themselves through their gravitational effects. The more we study double quasars, the more we realize just how much we still have to learn. They challenge our understanding of galaxy formation, black hole physics, dark matter, and even the nature of spacetime itself. Every discovery leads to new questions, and every unanswered question pushes us to look deeper into the unknown. And perhaps that is the greatest mystery of all, that the more we learn about the universe, the more we realize how much remains hidden. But as long as quasars continue to shine, we will keep searching for answers. Because somewhere out there, beyond the limits of our current knowledge, the secrets of double quasars are waiting to be uncovered. Double quasars are not just mysterious objects in the sky, they are cosmic beacons illuminating the very nature of our universe. They serve as laboratories for testing physics at extreme scales, providing insights into some of the most fundamental questions about black holes, galaxy evolution, and the large-scale structure of the cosmos. But their significance doesn't stop there. These rare celestial phenomena also offer a unique opportunity to study the interplay between gravity, time, and matter in ways that would be impossible in any terrestrial experiment. One of the biggest questions surrounding double quasars is how often they occur, and whether they are a relatively rare cosmic phenomenon, or a natural part of galaxy evolution. For decades, astronomers believed that double quasars were exceedingly rare, appearing only when two massive galaxies happen to collide in just the right conditions. However, recent surveys using the most powerful telescopes, such as the Hubble Space Telescope and the Very Large Telescope, have revealed that these events may be far more common than we once thought. Some researchers believe that nearly every massive galaxy in the universe has undergone a major merger at some point in its history, meaning that double quasars may have been a routine stage in galactic evolution. If this is true, it has profound implications for our understanding of how galaxies grow and change over time. It suggests that supermassive black holes are not just the end result of galaxy formation but an active and dynamic force shaping the cosmos. But if double quasars are so common, why do we see so few of them? Part of the reason is that they are incredibly difficult to detect. The light from quasars is so intense that, even when two are close together, their glow can blend into a single point when observed from Earth. It is only through the use of advanced techniques, such as gravitational lensing and high-resolution imaging, that scientists have been able to separate these light sources and confirm that they are indeed two distinct quasars rather than one. Even more fascinating is the way double quasars can be used to measure the expansion of the universe. Since their light can be split into multiple images by gravitational lensing, the time it takes for each image to reach us depends on the mass and shape of the lensing galaxy in between. By carefully analyzing these time delays, astronomers can measure the rate at which the universe is expanding, a key parameter in our understanding of cosmology. This method provides an independent way to calculate the Hubble constant, the value that describes how fast galaxies are moving away from us. Interestingly, studies of double quasars have led to some puzzling discrepancies in the measurement of the Hubble constant. Different methods of calculating this value have produced slightly different results, leading to what scientists call the Hubble tension. Some believe this discrepancy could be evidence that our understanding of dark energy, the mysterious force driving the acceleration of the universe, may need to be revised. Others speculate that unknown physics beyond our current models may be at play. But beyond these large-scale implications, double quasars also reveal insights into the chaotic environments of galaxies in the process of merging. When two galaxies collide, the gas and dust within them are violently stirred, leading to intense bursts of star formation. However, the energy released by the two growing supermassive black holes can also have a profound impact on their host galaxies, creating powerful winds and jets that can strip galaxies of their star-forming material. This process, known as quasar feedback, is thought to be one of the key mechanisms regulating galaxy evolution. Some of the largest elliptical galaxies in the universe are believed to have formed through this exact process. Two galaxies merging, their central black holes triggering powerful outflows of energy, and the resulting system eventually settling into a massive, quiescent galaxy. Double quasars provide a front-row seat to this process in action, giving us a glimpse of what may have happened billions of years ago in our own Milky Way's past. And yet, as much as we have learned from studying double quasars, they continue to surprise us. Some double quasars have been found at extreme distances, dating back to a time when the universe was less than 1 billion years old. These ancient systems challenge our models of how supermassive black holes form, as they appear to have grown to enormous sizes in a very short period. How did they accumulate so much mass so quickly? Did they form from the direct collapse of massive gas clouds, bypassing the slow process of stellar evolution? Or could they be the remnants of even older black holes formed in the very first moments of the universe? Theoretical models suggest that some of these double quasars may be precursors to even more exotic objects, such as binary supermassive black holes on the verge of merging. When two supermassive black holes spiral toward each other, they send out powerful ripples in spacetime known as gravitational waves. These waves were first detected in 2015 from merging stellar mass black holes, but detecting them from merging supermassive black holes remains one of the next great frontiers in astrophysics. If we could detect gravitational waves from double quasars, it would open up an entirely new way of studying these objects, not just by observing their light but by listening to the vibrations they send through the fabric of the universe. This would allow us to measure their masses, orbits, and ultimate fate in ways never before possible. The next generation of observatories, such as the Square Kilometer Array and LISA, may finally be able to capture these elusive signals, providing the final confirmation that these monstrous black holes are indeed merging. But what happens when they do merge? The collision of two supermassive black holes is one of the most energetic events in the universe, releasing more energy in gravitational waves than all the stars in the observable universe emit in light over the same period. It is thought that when these titanic objects finally combine, they produce a single, even more massive black hole that launches an enormous burst of energy, sending shockwaves through the surrounding galaxy. Some astronomers believe that these mergers could be responsible for some of the most energetic outbursts ever observed, including mysterious phenomena like fast radio bursts and even certain types of gamma-ray bursts. Others speculate that they could kick newly formed black holes out of their host galaxies entirely, sending them hurtling through intergalactic space as rogue black holes, moving at thousands of kilometers per second. The implications of double quasars stretch far beyond just black holes and galaxies. They force us to question the very nature of time and causality. When we look at a gravitationally lensed double quasar, we are seeing two versions of the same object, separated by time. In a way, we are looking into the past and the future of the same system simultaneously. What does this mean for our understanding of time itself? Could these observations provide hints about deeper, hidden structures in the universe? Some physicists have even speculated that the strange behaviors of double quasars might be linked to quantum mechanics on a cosmic scale. Could these objects be demonstrating a form of quantum entanglement across vast distances? Could their light be revealing hidden dimensions or alternative geometries of space-time? These ideas remain speculative, but they highlight just how much we still don't know about the universe. As we continue to push the boundaries of our understanding, double quasars stand as reminders that the cosmos is far more complex, mysterious, and awe-inspiring than we ever imagined. They challenge our theories, inspire new discoveries, and remind us that, no matter how much we learn, there will always be more to explore. And perhaps, somewhere in the depths of space, even more extreme and exotic objects are waiting to be found, objects that will once again change everything we thought we knew about reality itself. The mystery of double quasars is more than just an astronomical curiosity. It is a doorway into some of the deepest, most fundamental questions about the nature of the universe. As astronomers uncover more of these rare cosmic phenomena, each new discovery raises fresh questions about the forces shaping galaxies, black holes, and even space-time itself. These dual beacons of light, often separated by millions of light-years yet bound together in ways that defy simple explanations, serve as a cosmic puzzle that challenges our very understanding of the cosmos. One of the most mind-bending aspects of double quasars is their ability to act as cosmic time machines. Because light from these objects must travel for billions of years before reaching Earth, we are effectively looking into the past when we observe them. But due to the gravitational lensing effect, which bends and distorts light paths as they pass massive objects, we sometimes see the same quasar in multiple places at slightly different moments in time. This means that, in a single observation, we may be witnessing events that occurred years, decades, or even centuries apart. This is not just an odd quirk of physics, it is a profound insight into the nature of time itself. The idea that time is not absolute, but instead depends on gravity and perspective, was a revolutionary concept introduced by Einstein's theory of relativity. Double quasars provide one of the most striking real-world examples of this. In some cases, astronomers have observed variations in brightness between two images of the same quasar, and realized that one image is actually showing a slightly earlier stage of the quasar's activity. This effect allows scientists to essentially rewind and fast-forward cosmic events, gaining a deeper understanding of the life cycles of these powerful objects. But the strange relationship between double quasars and time goes even further. Some researchers believe that these objects could help us test the nature of dark matter and dark energy, the invisible components that make up the vast majority of the universe. By studying how the light from quasars is bent and delayed as it travels through space, astronomers can map the unseen mass distribution of the universe. In other words, quasars act as cosmic flashlights, illuminating the hidden structure of the cosmos. Recent discoveries suggest that some double quasars might be revealing evidence of something even more bizarre: cosmic strings. These hypothetical structures, predicted by certain models of the early universe, are thought to be ultra-thin, ultra-dense threads of energy stretching across space-time. If they exist, cosmic strings could warp space in ways that create unusual gravitational lensing effects, splitting light in ways that might mimic double quasars. Some astronomers speculate that at least a few of the objects we have identified as double quasars might actually be quasars duplicated by the presence of a cosmic string rather than two separate objects. If true, this would be one of the most groundbreaking discoveries in modern physics. Cosmic strings are thought to be remnants from the earliest moments after the Big Bang, and their detection would provide direct evidence for theories that attempt to unify quantum mechanics and general relativity. In other words, these quasars might not just be revealing the structure of galaxies, they could be exposing the deepest secrets of space-time itself. But even without cosmic strings, double quasars continue to defy expectations. Some recent observations have hinted at even more complex systems, where not just two but multiple quasars appear to be linked. These quasar clusters raise questions about whether certain regions of the universe are more prone to hosting these extreme objects. Could there be entire galaxies or cosmic neighborhoods where double quasars are common? If so, what does that say about the evolution of black holes and the formation of large-scale structures in the universe? Some of the most perplexing double quasar systems are those where the two quasars appear to be incredibly close together, sometimes separated by mere thousands of light-years, an almost impossibly small distance in cosmic terms. These cases suggest that the supermassive black holes powering the quasars are not just neighbors but are actively interacting. When two supermassive black holes get close enough, they begin a slow, spiraling dance toward each other, shedding energy in the form of gravitational waves. Eventually, they are expected to merge in an event so powerful that it would send ripples through the fabric of the universe. This kind of merger has never been directly observed, but double quasars provide crucial clues about how these events unfold. Scientists believe that in the final stages before a merger, the orbits of the black holes can warp and twist the surrounding spacetime so dramatically that time itself may behave in unexpected ways. Some models suggest that light escaping from the quasars may be stretched and distorted in ways we have never seen before, potentially allowing us to detect signs of an impending collision before it happens. As we enter an era of more advanced astronomical instruments, including the upcoming LISA, Laser Interferometer Space Antenna, mission designed to detect low-frequency gravitational waves, the study of double quasars could help pinpoint the exact moments when two supermassive black holes collide. If successful, we could witness one of the most violent and spectacular events in the universe, a direct confirmation of Einstein's predictions and a profound leap forward in our understanding of gravity itself. Yet, even with all this knowledge, one of the biggest mysteries remains: how did the first double quasars form? The standard model of galaxy formation suggests that supermassive black holes grow over billions of years, but some double quasars appear so early in the universe's history that their existence is difficult to explain. Did they form through an accelerated process that we have yet to understand? Were they created by direct collapses of primordial matter, skipping the usual stages of star formation? Or could they be evidence of an even more exotic process, such as remnants of an earlier universe that existed before the Big Bang? The possibility that some double quasars could be linked to a previous cosmic era is an idea that remains highly speculative but deeply fascinating. Some physicists have proposed that traces of a past universe might still be observable today, hidden in the oldest and most extreme objects. Could double quasars be among them? Could their strange, duplicated nature hint at some deeper, unresolved mystery about the fabric of reality itself? Ultimately, the study of double quasars is not just about understanding distant galaxies or black holes. It is about uncovering the fundamental principles that govern the universe. Every new discovery pushes the boundaries of what we thought was possible, revealing that the cosmos is more dynamic, more interconnected, and more mysterious than we ever imagined. And so, the hunt continues. With every new telescope, with every new survey of the sky, astronomers are finding more and more of these extraordinary objects. What other secrets might they hold? What unknown physics might they reveal? Could they be the key to solving some of the greatest unsolved problems in science? Perhaps, double quasars will not just teach us about the distant past, but about the ultimate fate of the universe itself. If black holes and quasars are part of a cycle that repeats across cosmic time, could they offer clues about what lies ahead? Could they help us predict how galaxies will evolve billions or even trillions of years from now? Or could they be the missing link in a grander, more mind-bending theory of the cosmos? One thing is certain: as long as there are mysteries in the sky, as long as there are unanswered questions about the universe, the study of double quasars will remain one of the most exciting frontiers in science. They are not just distant, glowing objects. They are cosmic time travelers, gravitational laboratories, and perhaps even keys to unlocking the deepest secrets of existence itself. The deeper we dive into the mystery of double quasars, the more we realize that these objects are more than just incredibly bright beacons in the distant universe. They are cosmic anomalies that challenge everything we think we know about black holes, galaxy formation, and even the fundamental nature of time and space. Their rarity alone makes them an object of intense study, but their implications stretch far beyond astronomy. These objects are living relics of an earlier universe, frozen in time yet constantly evolving, and they might be the missing puzzle pieces in some of the greatest scientific mysteries we have yet to solve. One of the most intriguing aspects of double quasars is how they seem to defy the traditional models of black hole growth. In most cases, astronomers assume that supermassive black holes at the centers of galaxies take billions of years to grow to their enormous sizes. They accumulate mass gradually, feeding on gas, dust, and even stars that wander too close. Yet, the discovery of double quasars in the early universe, some appearing just a few 100 million years after the Big Bang, raises a serious question: how did these black holes grow so quickly? The presence of two quasars in such close proximity suggests that their host galaxies may have collided at some point in the past, triggering a burst of rapid black hole growth. When galaxies merge, their central black holes are drawn toward each other, creating a chaotic gravitational environment that can funnel enormous amounts of gas toward them. This leads to the kind of intense feeding frenzy that fuels quasars, causing them to blaze with the energy of trillions of stars. But even this explanation doesn't fully account for some of the most extreme double quasar systems. Some of these objects are so distant, and therefore so old, that they seem to have formed at a time when the universe was still in its infancy. How did such massive black holes come into existence so soon after the Big Bang? Could it be that our understanding of black hole formation is missing a crucial piece? One possible explanation is that some of these early black holes didn't form from collapsing stars at all. Instead, they may have originated from direct gravitational collapses of vast clouds of primordial gas. If this theory is correct, then the first black holes in the universe could have been born with masses millions of times greater than the Sun, skipping the usual process of star formation entirely. This would explain why some double quasars appear far larger than they should be for their age. Even more bizarre is the possibility that some double quasars are not separate objects at all, but illusions created by the warping effects of gravity. This is where the concept of gravitational lensing becomes crucial. When light from a distant quasar passes through a massive galaxy or cluster of galaxies on its way to Earth, the intense gravitational field of the intervening matter bends and magnifies the light. In some cases, this effect can create multiple images of the same quasar, making it appear as if two identical quasars exist side by side. This raises an unsettling question: how many of the double quasars we have detected are actually real, and how many are mere optical illusions? Astronomers must carefully analyze each case to determine whether a double quasar is truly two separate objects, or a single quasar being distorted by gravitational lensing. This is no easy task, as the distances involved are so vast that even the most advanced telescopes struggle to distinguish between the two scenarios. If some double quasars are illusions, then it means our view of the distant universe is more distorted than we realize. It suggests that many of the objects we see in deep space are not where they appear to be, and that time itself is being stretched and manipulated in ways we are only beginning to understand. This brings us to one of the most mind-bending implications of double quasars: their potential connection to time loops and the deeper fabric of reality. The universe, according to Einstein's theories, is not a static, unchanging backdrop. It is a dynamic, ever-shifting entity where space and time are woven together into a single continuum. Gravity is not just a force pulling objects together, it is the warping of space-time itself. And in extreme gravitational environments, such as those surrounding supermassive black holes, time can behave in ways that seem completely alien to our everyday experience. If a double quasar system consists of two black holes orbiting each other, then the spacetime between them could be stretched and twisted into bizarre configurations. Some theoretical physicists suggest that in certain conditions, this could create a kind of time loop, a region where the past and future blur together, allowing for events to repeat or for information to travel in unexpected ways. Could some of the light we see from double quasars be coming from different points in time, rather than just different locations in space? This might sound like science fiction, but it is not entirely outside the realm of possibility. The mathematics of general relativity allow for scenarios where closed time-like curves, essentially, paths that loop back onto themselves in time, could exist in certain extreme gravitational conditions. If double quasars are creating such loops, they could be providing us with a glimpse into one of the most exotic phenomena in physics. But the mysteries don't stop there. Some double quasars exhibit strange spectral shifts, subtle changes in the wavelengths of their emitted light that cannot be easily explained by conventional models. These shifts might be caused by the intense gravitational interactions between the two quasars, or they could be signs of an even more exotic process. Some researchers have even speculated that these spectral anomalies could hint at the presence of unknown particles or forces acting on the quasars, potentially providing new insights into the nature of dark matter or even undiscovered aspects of physics. Another possibility that has intrigued scientists is the role of double quasars in shaping their cosmic environments. Quasars are not just passive objects, they are engines of enormous energy, blasting out powerful jets of radiation and particles that can influence entire galaxies. When two quasars exist in close proximity, their combined effects could be even more extreme, potentially altering the course of galaxy evolution on a massive scale. Could it be that some galaxies owe their very structure to the influence of ancient double quasars? Some evidence suggests that the powerful outflows from these systems could have played a key role in regulating star formation, either by stripping away gas and halting the birth of new stars or by triggering new bursts of star formation in surrounding regions. If this is true, then double quasars are not just cosmic curiosities. They are fundamental players in the grand story of how the universe has evolved over billions of years. And then there is the ultimate question: what happens when two quasars merge? If the black holes powering them are on a collision course, then they will eventually spiral inward, drawing closer and closer until they finally combine in a cataclysmic event unlike anything else in the cosmos. This merger would unleash a burst of gravitational waves so powerful that it would shake the very fabric of space-time itself, sending ripples across the universe that could be detected billions of light-years away. We have never directly witnessed such an event, but double quasars provide the best opportunity yet to study the final moments before a supermassive black hole merger. If we can observe these systems in their last stages, we might finally gain definitive proof of how these cosmic giants behave when they collide. The implications of this research could extend far beyond astrophysics, shedding light on the fundamental forces that govern the universe and perhaps even revealing new aspects of gravity that challenge our current understanding. Ultimately, the mystery of double quasars is not just about understanding distant objects. It is about uncovering the hidden rules that shape reality itself. These strange, enigmatic systems serve as windows into the deepest workings of the cosmos, offering glimpses into a universe that is far more complex, dynamic, and mysterious than we ever imagined. And as our telescopes and technologies improve, we may one day unlock the full secrets of these incredible objects, rewriting the very foundations of physics in the process. The quest to understand double quasars is more than just an astronomical curiosity. It is a journey into the unknown, where the very fabric of spacetime is stretched, twisted, and illuminated by the brightest beacons in the cosmos. These rare celestial phenomena challenge our most fundamental assumptions about black hole growth, galaxy evolution, and even the nature of time itself. Every new discovery about them forces us to rethink what we thought we knew, opening up profound new questions that may take generations to answer. One of the greatest challenges in studying double quasars is simply detecting them. Because quasars are already among the most distant and luminous objects in the universe, finding two in such close proximity is like searching for a flickering candle against the glare of a bonfire. Even the most advanced telescopes struggle to separate one from the other, and in many cases, what appears to be a single quasar may turn out to be two upon closer examination. To truly confirm the existence of a double quasar system, astronomers rely on multiple observational techniques. Spectroscopy is one of the most powerful tools in this effort. By analyzing the light from these objects, researchers can detect subtle shifts in wavelength caused by the motion of two quasars relative to each other. If the spectral lines exhibit periodic variations, it could indicate that the quasars are orbiting each other in a slow but inevitable dance toward merging. Another critical method is radio astronomy. Some double quasars emit powerful jets of radio waves, which can be detected even across vast cosmic distances. When two quasars exist in close proximity, their radio emissions can sometimes interfere with each other, creating distinctive patterns that betray their true nature. By mapping these signals with high-precision instruments, scientists can build detailed models of how the two quasars interact and evolve over time. However, perhaps the most fascinating aspect of double quasars is their connection to gravitational waves. When two supermassive black holes orbit each other, they gradually lose energy through the emission of these ripples in spacetime. Over millions of years, this process causes the black holes to spiral inward until they eventually collide in a cataclysmic event. The resulting explosion of gravitational waves would be one of the most powerful events in the universe, sending ripples through space that could be detected by future observatories. Currently, our ability to detect such signals is limited. Instruments like LIGO and Virgo can pick up gravitational waves from smaller black hole mergers, but supermassive black holes operate on far longer timescales, making their signals difficult to observe. However, future space-based detectors, such as the proposed LISA, Laser Interferometer Space Antenna, could revolutionize our understanding of these massive collisions. If we can catch a double quasar in its final moments before merging, we could witness one of the most extreme and energetic processes in the universe in real time. But what if the merger of two quasars doesn't just create gravitational waves? What if it also has profound consequences for the surrounding spacetime itself? Some theoretical models suggest that when two supermassive black holes collide, they could generate exotic phenomena, such as the creation of new spacetime structures or even the formation of microscopic wormholes. While this remains speculative, the idea raises intriguing possibilities about the role of double quasars in shaping the large-scale structure of the cosmos. Another mystery surrounding double quasars is their apparent connection to dark matter. Dark matter is one of the greatest unsolved problems in physics, an invisible substance that makes up most of the mass in the universe yet interacts only through gravity. Some researchers have proposed that double quasars could act as natural laboratories for studying dark matter, as their extreme environments may reveal subtle effects caused by this mysterious substance. For instance, if dark matter interacts with gravity in unexpected ways, it could influence the motion of the quasars in a double system. By carefully measuring their orbital dynamics, scientists might be able to detect deviations from expected behavior, providing new clues about the properties of dark matter. Additionally, the intense radiation from quasars could illuminate dark matter filaments that stretch across the universe, helping us map the invisible cosmic web that holds galaxies together. There is also the question of whether double quasars could play a role in cosmic inflation, the rapid expansion of the universe in its earliest moments. Some cosmologists have speculated that interactions between supermassive black holes in the young universe could have influenced the rate of inflation, creating variations in the cosmic microwave background radiation that we observe today. If this hypothesis is correct, then studying double quasars could help us unlock secrets about the very birth of the universe itself. Even more mind-bending is the possibility that some double quasars may be linked to alternate realities. According to certain interpretations of quantum mechanics and string theory, our universe may be just one of many in a vast multiverse. If so, then extreme gravitational interactions, such as those occurring in double quasar systems, could potentially create bridges between different universes, allowing for energy, or even information to leak between them. While there is currently no direct evidence for such phenomena, the study of double quasars is still in its infancy. As our telescopes and computational models improve, we may uncover evidence of effects that cannot be explained by conventional physics. If that happens, it could force us to rethink the very nature of reality, opening up possibilities that were once confined to the realm of science fiction. But even if double quasars do not lead us to new dimensions or reveal hidden forces of nature, they still represent one of the most fascinating frontiers in astrophysics. They are living fossils of the early universe, remnants of a time when the cosmos was still forming and black holes were just beginning their reign. By studying them, we are not just looking at distant objects, we are peering back in time, witnessing the echoes of events that shaped the universe as we know it. And so the mystery continues. With each new discovery, we edge closer to understanding the true nature of these cosmic beacons. But for every question we answer, new ones arise, pulling us deeper into the unknown. Perhaps the most thrilling aspect of double quasars is that they remind us of how much we still have to learn. The universe is vast, complex, and filled with surprises, and double quasars are one of its greatest enigmas, waiting for us to unravel their secrets. The deeper we delve into the mysteries of double quasars, the more we realize how interconnected they are with the very fabric of the cosmos. These rare celestial objects are more than just distant beacons of light. They are dynamic laboratories where extreme physics plays out on a scale that defies human comprehension. The immense gravitational forces at work in these systems shape not only the galaxies that host them but possibly even the evolution of the universe itself. One of the most puzzling aspects of double quasars is their formation. How do two supermassive black holes end up in such close proximity, both actively consuming matter and generating immense energy? The leading explanation involves galactic mergers. When two galaxies collide, their central black holes are drawn toward each other by gravity. Over time, they spiral inward, surrounded by a chaotic storm of gas and dust, until they settle into an orbit that places them just thousands or even hundreds of light years apart, a tiny distance on cosmic scales. However, this process is far from straightforward. The journey of these black holes toward each other is often slowed by interactions with the surrounding material. Gas and stars create friction, causing the black holes to lose energy and move closer together. Yet, simulations show that this process alone is not enough to make them fully merge within the age of the universe. There must be additional mechanisms at play, perhaps gravitational waves, additional galactic interactions, or even unseen forces that we have yet to discover. Another key mystery is the rate at which double quasars form. Given how many galaxies are known to merge, one would expect double quasars to be fairly common. Yet, they remain exceedingly rare. Some scientists speculate that many galactic mergers occur without their central black holes becoming active quasars at the same time. Others believe that some double quasars may be hidden from view, shrouded in thick clouds of gas that block their light from reaching us. This raises an intriguing possibility. Could there be double quasars lurking in the darkness, invisible to our current instruments? If so, they might be far more numerous than we realize, quietly influencing the evolution of their host galaxies. Future telescopes, especially those designed to detect infrared and radio emissions, may help us uncover these hidden objects, providing a clearer picture of how common double quasars truly are. One of the strangest implications of double quasars involves their relationship with time itself. Because quasars are so distant, their light takes billions of years to reach us. This means that when we observe a double quasar, we are seeing it as it was in the past, often at a time when the universe was far younger than it is today. In some cases, gravitational lensing can create the illusion that we are seeing the same quasar in multiple locations, as its light is bent and split by massive objects in the foreground. This effect has led to speculation that some supposed double quasars might actually be single quasars viewed at different points in time. If a quasar's light is bent by an intervening galaxy, the different paths the light takes could mean that we are seeing two images of the same object, but from different moments in its history. If true, this would mean that some double quasars are not actually pairs at all, but rather a strange illusion caused by the warping of spacetime itself. The study of double quasars has also led to unexpected discoveries about the nature of supermassive black holes. Traditionally, astronomers believed that black holes grew gradually over time, slowly accumulating mass as they devoured gas and stars. However, observations of double quasars suggest that some black holes may experience sudden bursts of rapid growth, triggered by their interactions with a companion. When two supermassive black holes come close together, they can stir up surrounding gas, funneling vast amounts of material into their accretion disks. This process could explain why some quasars appear to shine far brighter than expected, temporarily outshining even their entire host galaxies. But this raises an even bigger question. If black holes can grow rapidly in double quasar systems, could some of the most massive black holes in the universe have formed this way? The largest black holes, known as ultramassive black holes, can reach tens of billions of times the mass of the Sun. Their origin remains a mystery, as standard models struggle to explain how they could have accumulated so much mass in the time available. Some researchers now propose that repeated mergers of double quasars may be responsible, gradually building up these cosmic giants over billions of years. Another intriguing mystery involves the jets of energy that some double quasars produce. Many quasars emit powerful streams of charged particles that travel at nearly the speed of light, extending for thousands, or even millions of light years. In some cases, these jets appear to interact in unexpected ways when two quasars are in close proximity. Could the magnetic fields of two quasars become entangled, creating strange and unpredictable effects? Could the jets of one quasar influence the growth and activity of its companion? Some scientists speculate that these jets might even serve as cosmic triggers, accelerating star formation in surrounding gas clouds. If true, this would mean that double quasars are not just consuming matter, they are also playing a role in the creation of new stars, actively shaping the evolution of their galaxies in ways we are only beginning to understand. Even more mysterious is what happens when a double quasar finally merges into a single black hole. As the two objects spiral toward each other, their combined gravitational forces can create a phenomenon known as a kick, where the newly merged black hole is violently ejected from its host galaxy. If the kick is strong enough, the black hole may be flung into intergalactic space, forever drifting alone without a home. Such rogue black holes could be common in the universe, yet incredibly difficult to detect. Some astronomers believe that studying double quasars in their final stages could provide the best opportunity to catch a black hole in the process of being ejected. If we ever observe a double quasar where one black hole suddenly vanishes, it could be direct evidence that these cosmic monsters sometimes get kicked out of their galaxies. And what about the final moments before a merger? When two supermassive black holes collide, they release an unimaginable amount of energy, not just in the form of gravitational waves, but also through bursts of electromagnetic radiation. Some simulations suggest that such an event could produce a flash of light visible across the entire universe, outshining all the stars in a galaxy for a brief moment. If we could detect one of these events in real time, it would be one of the most significant discoveries in the history of astronomy. It would confirm theories about how supermassive black holes grow and evolve while providing a direct test of Einstein's general theory of relativity. Some researchers are already scanning the sky for signs of such a merger, hoping to catch a glimpse of the ultimate cosmic collision. Yet, for all we have learned, double quasars remain a mystery wrapped in layers of complexity. They challenge our understanding of gravity, time, and even the nature of the universe itself. Each new discovery brings fresh questions, pushing the boundaries of what we thought was possible. What other secrets do they hold? Could they be hiding clues about the true nature of dark matter, the origins of the universe, or even new physics that we have yet to comprehend? As our technology improves, our ability to study double quasars will only grow. New telescopes, more powerful simulations, and better methods of detecting gravitational waves will allow us to peer deeper into these enigmatic systems than ever before. And with each new breakthrough, we will come one step closer to unraveling one of the greatest cosmic mysteries of all time. The more we study double quasars, the more we realize that they are not just rare cosmic oddities but crucial pieces in the puzzle of the universe. These extraordinary systems provide insights into the forces that shape galaxies, the behavior of supermassive black holes, and even the fundamental nature of space and time. Yet, despite all the progress we've made, many of their mysteries remain unsolved. One of the biggest challenges in studying double quasars is identifying them in the first place. Because they are so far away, their light is often distorted by the vast cosmic distances it travels. In many cases, double quasars appear as single points of light in our telescopes, making it incredibly difficult to tell whether we're looking at one object or two. Even when astronomers suspect that a quasar might have a twin, confirming it requires a combination of advanced techniques, including spectroscopy, gravitational lensing analysis, and radio imaging. Gravitational lensing has been particularly useful in uncovering double quasars. When a massive object, such as a galaxy, sits between Earth and a distant quasar, its gravity bends and distorts the quasar's light, sometimes splitting it into multiple images. In some cases, what appears to be a double quasar is actually just a single quasar whose light has been duplicated by this effect. However, in other cases, two distinct quasars are caught in the same gravitational lens, creating an even more complex optical illusion. By carefully analyzing the light coming from these systems, astronomers can determine whether they are looking at a true pair of quasars or just a trick of gravity. Another major mystery surrounding double quasars is the role they play in galaxy evolution. We know that quasars are powered by supermassive black holes consuming surrounding material, and we also know that nearly every large galaxy has a supermassive black hole at its center. But what happens when two of these powerful objects exist in the same galaxy? Does their combined energy trigger bursts of star formation, or does it rip apart the galaxy from within? Some simulations suggest that double quasars might be responsible for some of the most extreme transformations galaxies undergo. When two black holes are actively feeding in the same galaxy, their combined radiation can heat up surrounding gas, preventing new stars from forming. At the same time, the turbulence they create might compress gas clouds in other regions, sparking waves of rapid star formation. This push and pull effect could determine the fate of an entire galaxy, either fueling its growth or cutting off its ability to form new stars for billions of years. Even more intriguing is the question of what happens to double quasars over time. We know that the black holes powering them are gradually moving closer together, but how long does this process take? Some studies suggest that it could take billions of years for two supermassive black holes to merge, while others propose that certain conditions could accelerate the process dramatically. If two black holes are surrounded by dense clouds of gas, friction might cause them to spiral inward much faster. If they are in a crowded region of space, interactions with other stars and black holes could also speed up their merger. But what happens when two supermassive black holes finally collide? The event would unleash an incomprehensible amount of energy, creating a burst of gravitational waves that would ripple across the universe. These waves, distortions in spacetime itself, have been detected from smaller black hole mergers, but a collision between two supermassive black holes would be on an entirely different scale. Scientists believe that such an event could briefly outshine all the stars in a galaxy, producing an explosion of energy visible across vast cosmic distances. Yet, detecting such an event is easier said than done. The signals produced by merging supermassive black holes are different from those detected by current gravitational wave observatories like LIGO and Virgo, which are designed to catch smaller-scale mergers. To truly observe the final moments of a double quasar merging, we need new kinds of observatories, ones that can pick up the low-frequency gravitational waves produced by these colossal collisions. Projects like the Laser Interferometer Space Antenna, LISA, are being developed to do just that, promising to open a new window into the universe and potentially allowing us to witness the moment when two supermassive black holes become one. But what if some double quasars never merge at all? What if certain conditions cause them to remain locked in an endless orbital dance, forever circling each other without ever colliding? Some models suggest that in certain cases, the energy required to bring two black holes together simply isn't there. Instead, they might remain in a stable orbit, continuing to shine as double quasars indefinitely. If this is true, there could be ancient double quasars that have existed since the early universe, still locked in their gravitational embrace billions of years later. And what if the most distant double quasars hold secrets about the origins of black holes themselves? One of the biggest unsolved mysteries in astrophysics is how the first supermassive black holes formed so quickly after the Big Bang. Some theories suggest that they grew from smaller black holes that merged over time, while others propose that they formed directly from collapsing clouds of gas. If we could find double quasars from the earliest epochs of the universe, they might provide crucial clues about which of these theories is correct. Double quasars are more than just astronomical curiosities. They are natural laboratories for studying the most extreme forces in the cosmos, from the physics of black holes to the mechanics of galaxy formation. They challenge our understanding of gravity, light, and even time itself. Every new discovery about these enigmatic objects brings us one step closer to unlocking some of the universe's deepest secrets. And yet, the more we learn, the more questions arise. Are there entire populations of double quasars hidden from view, waiting to be discovered? Could some of them be harboring exotic forms of matter or even new physics beyond our current understanding? What will we learn when we finally witness the merger of two supermassive black holes in real time? The search for answers continues, and with every new observation, the universe reveals just a little bit more of its grand design. But for now, double quasars remain one of the greatest mysteries of space, distant beacons of light that defy explanation, illuminating not only the depths of the cosmos but also the limits of human knowledge. The mysteries surrounding double quasars run deeper than we ever imagined. These enigmatic celestial phenomena do not just challenge our understanding of astrophysics. They force us to rethink the very nature of space, time, and the evolution of the universe itself. Despite all of our advancements in technology, double quasars continue to elude complete comprehension, leaving astronomers and physicists with more questions than answers. One of the most perplexing questions is, how many double quasars exist in the observable universe? Given their extreme luminosity, one might assume that they would be relatively easy to spot. However, their detection is complicated by a variety of factors. First, they are often located billions of light years away, meaning we are seeing them as they were in the distant past. Second, many of them are hidden behind thick clouds of dust and gas, which obscure their light from our telescopes. Third, the vast distances involved mean that their light is stretched and redshifted due to the expansion of the universe, making it difficult to distinguish them from other cosmic objects. But perhaps the biggest challenge in identifying double quasars is that they often masquerade as single quasars. Because they exist in close proximity to each other, the light from both can blend together, fooling astronomers into thinking they are looking at just one object. This means that many of the quasars we have already discovered might actually be doubles in disguise. Only through detailed spectroscopic analysis and high-resolution imaging can we determine whether a quasar has a hidden twin. To make matters even more complicated, there is a possibility that some double quasars are not true binaries at all but rather gravitationally lensed illusions. When light from a distant quasar passes through a massive galaxy or cluster on its way to Earth, it can be bent and split into multiple images, creating the appearance of two or more quasars when, in reality, there is only one. Distinguishing between genuine double quasars and lensed quasars requires an in-depth study of their spectral signatures, variability patterns, and the surrounding gravitational environment. But let's say we do manage to confirm the existence of a double quasar. What does this tell us about the galaxy in which it resides? One of the leading theories is that double quasars form when two galaxies collide and merge. When two galaxies come together, their central black holes are pulled toward each other, forming a binary system. During this process, vast amounts of gas and dust are funneled toward the black holes, igniting their quasar activity. This means that whenever we find a double quasar, we are likely witnessing a galaxy in the middle of a dramatic transformation, one that will ultimately shape its future. This raises another fascinating question: what happens to the stars, planets, and other celestial bodies that exist in a galaxy undergoing such a violent process? The sheer gravitational forces at play in a merging galaxy are enough to send stars careening into deep space, ejecting them at such high velocities that they become what are known as hypervelocity stars, stars that travel so fast they escape their home galaxy entirely. Other stars might be pulled into the gravitational well of the merging black holes, where they are torn apart by tidal forces, adding to the chaos. And what about planetary systems? If our own galaxy were to undergo a merger like this, what would happen to Earth? Would we be flung out into intergalactic space, or would we remain relatively unaffected? While the vast distances between stars mean that direct collisions are unlikely, the gravitational disturbances caused by a galaxy merger could drastically alter the orbits of planets, potentially sending some hurtling into their parent stars while others are ejected from their solar systems entirely. But let's return to the double quasars themselves. As they continue their slow but inevitable dance toward each other, their fate is sealed. They will merge. However, the timeline for this process remains one of the biggest mysteries in astrophysics. Some models suggest that it takes hundreds of millions, if not billions, of years for two supermassive black holes to spiral inward and collide. Others propose that under the right conditions, the merger could happen much more quickly, particularly if there is an abundance of gas and other material to act as a braking force. If and when they do merge, the consequences will be spectacular. The event will unleash an unimaginable amount of energy in the form of gravitational waves, ripples in the fabric of spacetime itself. Unlike the gravitational waves detected by LIGO and Virgo, which come from the mergers of smaller black holes or neutron stars, the waves produced by a supermassive black hole merger will have wavelengths so long that they cannot be detected with current technology. Instead, astronomers are developing new tools, such as the Laser Interferometer Space Antenna, LISA, to pick up these signals. But there's another mystery lurking in the aftermath of such a merger. What happens to the newly formed, even larger black hole? In some cases, it might settle quietly at the center of its galaxy, continuing to feed on surrounding matter. However, there are scenarios in which the merged black hole receives a powerful kick from the gravitational waves it emits, sending it hurtling through space at thousands of kilometers per second. If this happens, the black hole could actually be ejected from its home galaxy entirely, becoming what is known as a rogue black hole, a supermassive black hole drifting alone through intergalactic space. If such an event were to occur, it could have profound consequences for the galaxy left behind. A galaxy without a central black hole might struggle to regulate star formation, leading to an overabundance of new stars or, conversely, a sudden halt in star formation altogether. The effects of such an event could reshape an entire galaxy, potentially changing its evolutionary trajectory for billions of years. But perhaps the most mind-bending question of all is whether double quasars could provide evidence for physics beyond our current understanding. Could they harbor clues about the nature of dark matter, dark energy, or even extra dimensions? Some physicists speculate that extreme gravitational environments like those found around double quasars might allow us to test theories of quantum gravity, giving us insights into the fundamental structure of reality itself. And then there's the possibility that double quasars could serve as beacons for advanced extraterrestrial civilizations. If an intelligent species were to harness the immense energy output of a quasar, they might use it as a power source or even as a means of interstellar communication. Some scientists have suggested that unusual patterns in quasar light curves could be the result of artificial tampering, though, as of yet, no conclusive evidence has been found. Ultimately, the mysteries of double quasars remind us just how little we truly understand about the universe. Each discovery leads to new questions, and every answer seems to reveal even deeper layers of complexity. As our technology improves and our ability to peer into the cosmos expands, we may one day unravel the full story of these incredible cosmic objects. Until then, double quasars will remain some of the most fascinating and perplexing phenomena in all of astronomy, shining as distant enigmas in the vast, infinite darkness of space. The more we investigate double quasars, the more we realize that they might hold the key to answering some of the universe's most perplexing questions. One of the biggest mysteries in cosmology is how galaxies and black holes evolve over time. We know that most large galaxies have supermassive black holes at their centers, but the question of how these behemoths grow so massive remains an ongoing puzzle. Double quasars offer a rare glimpse into this process, allowing us to observe what happens when two supermassive black holes interact in the early universe. The key to understanding this lies in the immense gravitational forces at play. When two galaxies merge, their central black holes begin orbiting each other, drawing in vast amounts of gas and dust. This violent process generates enormous amounts of energy, turning both black holes into active quasars. But the real mystery lies in what happens next. Over time, these black holes should spiral inward, eventually merging into a single, even more massive black hole. However, theoretical models predict that there should be a significant delay in this process due to a phenomenon known as the final parsec problem. The final parsec problem is one of the greatest challenges in astrophysics. It suggests that once two black holes get close enough, about 3 light-years apart, they should slow down due to a lack of nearby matter to transfer their energy away. If this is true, then many double quasars should exist in this stalled state for billions of years, unable to complete their merger. But observational evidence suggests otherwise. Some double quasars appear to merge far faster than expected, leading to questions about what additional forces might be at work. One possibility is that surrounding gas and stars act as a bridge, allowing the black holes to continue losing energy and spiral inward at a much faster rate. Another theory suggests that interactions with dark matter might play a role. If dark matter particles exist in large halos around galaxies, their gravitational influence could accelerate the merger process in ways we don't yet fully understand. This raises an even bigger question: could studying double quasars help us uncover the true nature of dark matter? Dark matter remains one of the most elusive substances in the universe. We know it exists because of its gravitational effects on galaxies, but we have yet to directly detect it. If double quasars are merging faster than expected, it could be a sign that dark matter is interacting with them in ways we never anticipated. Some physicists speculate that dark matter might form dense, invisible clouds around merging galaxies, providing the necessary gravitational drag to speed up black hole mergers. Others believe that dark matter could behave in a way that's completely different from anything in the standard model of physics, potentially even hinting at new fundamental forces. But what if double quasars are revealing something even stranger? There's a possibility that these extreme environments could be testing grounds for exotic physics, such as wormholes or extra dimensions. Some theories suggest that when two supermassive black holes get close enough, the intense gravitational distortions could create shortcuts through spacetime. If true, these cosmic tunnels could be gateways to entirely different regions of the universe, or even other universes. While there's no solid evidence yet, some astronomers are beginning to look for unusual signals that might hint at such phenomena. And then there's the idea that double quasars might not just be merging black holes, but something even more extreme: primordial black holes. Unlike regular black holes, which form from collapsing stars, primordial black holes are thought to have formed in the first moments after the Big Bang. If some of these ancient black holes survive to the present day, they might be lurking in double quasars, waiting to be discovered. Some scientists even speculate that primordial black holes could make up a significant portion of dark matter itself. If so, studying double quasars could be the key to proving their existence once and for all. But perhaps the most astonishing possibility is that double quasars could provide a glimpse into the fate of our own galaxy. The Milky Way is currently on a collision course with the Andromeda Galaxy, a massive spiral galaxy that is moving toward us at about 110 kilometers per second. In about 4.5 billion years, the two galaxies will merge, creating a new supergalaxy sometimes referred to as Milkomeda. When this happens, the supermassive black holes at the centers of both galaxies will also begin their slow, inevitable journey toward collision. If humanity still exists at that time, our distant descendants might witness the formation of a double quasar in our own cosmic backyard. What would that look like from Earth? If the merger were to happen while the black holes were still actively feeding, we would see an incredibly bright, dual-lobed quasar shining in the sky, far brighter than anything we've ever observed. The gravitational waves from the eventual merger would ripple across the galaxy, stretching and squeezing space itself. If advanced civilizations exist elsewhere in the cosmos, they, too, would detect these signals, potentially using them as a way to study the physics of black holes. But there's one more possibility that cannot be ignored. What if double quasars are not just naturally occurring phenomena but artificially manipulated objects? Some theorists have proposed that highly advanced civilizations, what physicists call Kardashev-type 3 civilizations, could harness the energy of quasars for their own purposes. If such civilizations exist, they might use double quasars as massive energy sources, gravitational slingshots, or even beacons to communicate across intergalactic distances. Could some of the strange behaviors we observe in double quasars actually be the result of intelligent intervention? While there is no evidence to support this idea yet, the mere possibility is enough to spark the imagination. If double quasars are being used in ways we don't yet understand, it could mean that we are not alone in the universe, and that highly advanced civilizations have been shaping the cosmos in ways we have yet to comprehend. Double quasars represent one of the greatest mysteries in modern astronomy. They challenge our understanding of black holes, galaxy evolution, dark matter, and even the fundamental nature of spacetime itself. Each discovery brings us closer to unraveling their secrets, but at the same time, new questions continue to emerge. As telescopes grow more powerful and new observational techniques are developed, we may finally be on the verge of uncovering the full story behind these cosmic enigmas. Until then, they remain as some of the brightest, most fascinating, and most mysterious objects in the universe, silent witnesses to the violent and beautiful processes that have shaped our cosmos for billions of years. The more we peer into the cosmos, the more double quasars challenge everything we thought we knew. Every time astronomers detect a new pair, they have to ask, is this just a chance alignment, or are we truly witnessing two supermassive black holes locked in an epic cosmic dance? This question isn't just about classification, it's about how we interpret the fundamental forces shaping the universe. Because if we misidentify double quasars, we might be missing critical clues about black hole mergers, gravitational waves, and even the large-scale structure of the cosmos itself. One of the biggest challenges in studying double quasars is simply proving they exist. Since we're dealing with objects that are billions of light years away, even the most powerful telescopes struggle to distinguish whether we're seeing two separate black holes or just one quasar with an unusual structure. Many single quasars exhibit odd flickering patterns, giving the illusion of multiple light sources when in reality, we're just looking at a single chaotic accretion disk. So how do astronomers tell the difference? The key lies in how light behaves. When two quasars are genuinely separate objects, they should have distinct spectra, different shifts in their light due to their relative motion. This is where spectroscopic analysis comes into play. By studying the tiny variations in how each quasar emits light, researchers can determine whether they are two separate objects or just one masquerading as two. But even this method has its limits. If the quasars are too close together, their spectra can blend, making it nearly impossible to separate them. That's why astronomers rely on gravitational lensing, one of the most mind-bending phenomena in physics. When light from a distant object passes near a massive galaxy, the intense gravitational field bends and magnifies the light, creating duplicate images. This effect, predicted by Einstein's general relativity, can make one quasar appear as two, tricking us into thinking we're seeing a double quasar when we're actually witnessing a cosmic mirage. But if we analyze how the images change over time, we can often distinguish a true pair from a gravitationally lensed illusion. But what if some double quasars are more than just black holes? What if, buried among them, we are actually seeing something far stranger, objects that defy conventional astrophysics? Some researchers have proposed that a fraction of observed double quasars could actually be exotic astrophysical phenomena, such as boson stars, which are hypothetical objects made of ultralight particles that could mimic the behavior of black holes without having an event horizon. Others speculate that some of these mysterious quasars might even be cosmic strings, thin, incredibly dense filaments of energy left over from the early universe. If even one such object were confirmed, it would revolutionize physics as we know it. And then there's the time factor. When we observe a double quasar, we're not just seeing it as it is now, we're looking billions of years into the past. This means that many of the double quasars we detect may have already merged into single black holes long before Earth even formed. In essence, they are cosmic fossils, frozen in time, offering us a window into a universe that no longer exists. This leads to a profound realization. If double quasars can tell us about the past, could they also offer a glimpse into the future? If we refine our ability to study them, we might one day predict the fates of galaxies yet to merge. We could even use them as a kind of natural laboratory to test what will happen when our own Milky Way and Andromeda galaxies collide. This isn't just theoretical curiosity. It has real implications for the long-term survival of our galaxy and the solar system itself. As Andromeda and the Milky Way spiral toward each other, their central black holes will follow suit. Will they form a new double quasar, lighting up the sky with unimaginable brilliance? Will their merger produce a burst of gravitational waves powerful enough to disrupt the fabric of space-time? Could the Sun and its planets be ejected from the galaxy entirely due to the chaotic gravitational interactions? We don't yet know the answers, but double quasars might hold the key. One final possibility that remains tantalizingly open is whether double quasars could provide direct evidence of new physics. Right now, our understanding of black hole mergers is based on Einstein's general relativity. But what if these events actually reveal inconsistencies in the theory? Some physicists suspect that at extreme scales, relativity might break down, requiring an entirely new framework, perhaps one that unifies gravity with quantum mechanics. If double quasars exhibit behavior that contradicts our current models, they could be the missing link in one of the greatest scientific puzzles of all time. The universe is still hiding its deepest secrets, and double quasars may be among the most cryptic of them all. Whether they reveal the nature of dark matter, the fate of galaxies, or even entirely new forms of matter and energy, one thing is certain: they are among the most powerful, enigmatic, and awe-inspiring objects in existence. Every time we study one, we are peering into a realm where the laws of physics are pushed to their absolute limits, where time, space, and energy collide in ways we can barely comprehend. And as our technology advances, we may soon find ourselves on the brink of discoveries that could change our understanding of reality itself. As we continue to unravel the mysteries of double quasars, we must consider the role they play in the grand cosmic dance of galaxies. Every double quasar is a signpost of a much larger process, the collision and merging of entire galaxies. This isn't just a random event, it's a fundamental mechanism by which the universe evolves. Galaxies do not remain static. They are constantly interacting, merging, and reshaping the cosmic landscape. And at the heart of many of these mergers, we find supermassive black holes, some of which manifest as double quasars before they ultimately merge into a single, even more massive entity. The scale of these interactions is almost impossible to grasp. Imagine two galaxies, each containing hundreds of billions of stars, interstellar gas, dark matter, and at their centers, two incomprehensibly dense black holes, each millions or even billions of times the mass of the Sun. Over millions of years, these two galaxies spiral toward each other, their gravitational forces warping and distorting the very fabric of spacetime. The interstellar gas is compressed and heated, triggering bursts of star formation, so-called starburst galaxies. are often the precursors to double quasar systems. As the black holes draw closer, they start to interact, their immense gravity creating tidal forces that can fling stars across the cosmos and distort entire galactic structures. And then, the inevitable happens. The two black holes get close enough to form a binary system. This is where double quasars come into play. At this stage, both black holes are actively consuming matter, each generating an accretion disk and emitting blinding amounts of radiation. From Earth, if we have the right perspective, we see them as two quasars in close proximity, shining with an intensity that outshines the rest of their host galaxy. But this phase is temporary. The dance continues, and as the two black holes spiral inward, their orbit tightens. Here's where things get even more mind-bending. As these binary black holes continue their approach, they begin to lose energy through gravitational waves, ripples in spacetime first predicted by Einstein and confirmed only recently through direct detection. These waves carry away angular momentum, causing the black holes to close the gap between them even faster. Eventually, they will merge in a cataclysmic event, releasing a final burst of gravitational waves so powerful that they can be detected across billions of light years. What happens next? The newly merged black hole stabilizes, but sometimes it can experience a phenomenon called a black hole recoil. If the merger is asymmetric, if one black hole was spinning faster than the other, or if their masses were significantly different, the final black hole can be ejected from its galaxy entirely, hurtling through space as a so-called rogue black hole. There is even evidence suggesting that some of these rogue black holes may still carry accretion disks with them, continuing to shine as they drift through intergalactic space. If such objects exist, they would be some of the strangest entities in the universe. Black holes without a home, wandering through the void between galaxies, still radiating energy from their long-dead pasts. But even for those black holes that remain within their galaxies, the consequences of their mergers are profound. The energy released in the process can have ripple effects that shape the evolution of their surroundings. Enormous amounts of radiation can be unleashed, sometimes triggering, or quenching, star formation across the galaxy. This feedback process is one of the main reasons galaxies have the shapes and sizes they do today. In essence, every double quasar we observe is not just an astronomical curiosity but a crucial piece of the puzzle in understanding how galaxies grow, change, and die. And then there's the question of what happens inside the black hole once the merger is complete. According to general relativity, anything that crosses the event horizon of a black hole is lost forever, crushed into a singularity of infinite density. But what if that's not the whole story? Some physicists have proposed alternative theories that suggest black holes might not contain singularities at all. Instead, they could be fuzzballs, regions of extreme quantum fluctuations where the laws of physics as we understand them break down. Others speculate that black holes might actually be gateways to other regions of the universe or even entirely separate universes. If any of these ideas prove true, double quasars might be far more than just markers of galaxy evolution. They could be clues to a deeper reality, one that transcends our current understanding of physics. One thing is certain, the more we study double quasars, the more questions they raise. Could they help us refine our models of gravitational waves? Could they reveal unknown physics lurking in the depths of black hole mergers? Could they offer evidence of exotic forms of matter, or even hint at the nature of dark matter and dark energy? These are not just theoretical musings. They are active areas of research, ones that could redefine how we see the cosmos. With future telescopes like the James Webb Space Telescope and upcoming next-generation observatories, we will gain even more precise measurements of double quasars. These instruments will allow us to detect fainter, more distant quasars, perhaps even glimpsing them in the earliest epochs of the universe. And with new gravitational wave detectors coming online, we may soon be able to link the electromagnetic signals from quasars with the ripples in spacetime caused by their mergers, giving us an unprecedented view into one of the most extreme processes in existence. But as with all great scientific discoveries, the more we learn, the more we realize how much remains unknown. Double quasars may be a window into the distant past, a signpost of galaxy mergers, and a key to understanding black hole evolution. but they may also hold deeper secrets that we have yet to uncover. And if history is any indication, the universe is always ready to surprise us. As we push deeper into the mysteries of double quasars, it becomes clear that these phenomena are not just rare cosmic curiosities. They are essential keys to unlocking some of the universe's most profound secrets. Every observation of a double quasar provides us with a snapshot of an ancient, violent process that has shaped the galaxies we see today. These celestial beacons are so far away that studying them is like looking back in time, to an era when the universe was younger, galaxies were still forming, and black holes were just beginning their endless consumption of matter. But beyond their role in shaping galaxies, double quasars also offer a unique opportunity to test our understanding of the laws of physics on the grandest scales possible. One of the most intriguing aspects of double quasars is their potential to serve as natural laboratories for studying gravity. According to Einstein's general theory of relativity, extremely massive objects warp the spacetime around them. This effect, known as gravitational lensing, allows us to observe light bending around massive objects, sometimes creating multiple images of a single source. When we observe a double quasar, it's crucial to determine whether we're looking at two separate black holes or a single quasar being gravitationally lensed by an intervening galaxy. In cases where gravitational lensing is involved, the images of the quasar may appear slightly different due to the time delay in the light's journey. This effect not only helps confirm whether we are indeed observing a true double quasar but also provides a powerful way to measure the expansion rate of the universe. Gravitational lensing of quasars has already been used to refine estimates of the Hubble constant, the value that describes how fast the universe is expanding. The problem is, different methods of measuring the Hubble constant have led to slightly different results, creating what astronomers call the Hubble tension. If double quasars observed through gravitational lensing can help resolve this discrepancy, they could revolutionize our understanding of cosmic expansion. But even if they don't fully solve the mystery, they will certainly provide new data points that will push our models forward. Beyond gravitational lensing, double quasars are also helping scientists probe the environments around supermassive black holes in ways that were never before possible. When two quasars exist in close proximity, their intense radiation interacts in complex ways, influencing the gas, dust, and magnetic fields around them. This interaction can give rise to powerful relativistic jets, streams of charged particles moving at nearly the speed of light, that shoot out from the poles of the black holes. Studying these jets can reveal how black holes convert gravitational energy into powerful electromagnetic radiation. Additionally, observing the spectral lines of the light emitted from double quasars can provide insight into the composition of the intergalactic medium, the diffuse gas that exists between galaxies and plays a crucial role in cosmic evolution. But perhaps the most fascinating aspect of double quasars lies in their potential to shed light on one of the biggest unsolved mysteries in physics: dark matter. Dark matter is an invisible substance that makes up most of the matter in the universe, yet it does not emit, absorb, or reflect light, making it extremely difficult to detect directly. However, its presence is inferred from its gravitational effects on galaxies and other cosmic structures. When two quasars exist near each other, their light must pass through vast stretches of space before reaching us. If dark matter is clumped in certain ways, it could slightly distort the paths of light, creating subtle signals that astronomers can analyze. By mapping these distortions, double quasars could provide a new way to detect dark matter and understand its distribution across the universe. Another exciting possibility is that double quasars could serve as testing grounds for exotic physics beyond the standard model. Some theories propose that dark matter is made up of hypothetical particles called axions, which could affect the polarization of light passing through them. If double quasars exhibit unusual polarization patterns that cannot be explained by conventional physics, they could provide indirect evidence for the existence of these strange particles. Similarly, double quasars could help test alternative theories of gravity, including modifications to general relativity that attempt to explain cosmic acceleration without invoking dark energy. And then there is the question of time. Some physicists speculate that black holes might not be the one-way cosmic prisons we think they are. Instead, they might be connected to other regions of the universe through hypothetical structures called wormholes. If double quasars are actually linked by wormholes rather than being separate objects, it would challenge everything we know about spacetime and causality. While this idea remains purely speculative for now, it is precisely these kinds of mind-bending possibilities that make the study of double quasars so exciting. Looking forward, the future of double quasar research is brighter than ever. Upcoming telescopes, including the Vera C. Rubin Observatory and the Extremely Large Telescope, ELT, will be able to detect even fainter double quasars, potentially revealing new populations of these rare objects. The Laser Interferometer Space Antenna, LISA, a planned gravitational wave detector set to launch in the 2030s, may even be able to detect the final in-spiral and merger of double quasars, providing an entirely new way to study these cosmic collisions. Double quasars are far more than just distant points of light in the sky. They are cosmic lighthouses, illuminating the hidden forces that shape the universe. They challenge our understanding of black holes, test the limits of general relativity, provide clues about dark matter, and may even offer hints about new physics waiting to be discovered. With each new observation, we move one step closer to answering some of the deepest questions in astrophysics. But as is always the case with the cosmos, every answer only leads to more questions. And that is the true beauty of space mysteries. There is always more to discover, more to explore, and more to understand. Double quasars are not just cosmic anomalies. They are living records of the universe's violent past, each one a signpost pointing toward fundamental truths that are still waiting to be uncovered. But as we push deeper into this mystery, the most pressing question remains: how do these enigmatic systems form? If we can understand the origins of double quasars, we might gain insight into the most extreme environments in the universe, the evolution of galaxies, and even the behavior of spacetime itself. One of the most widely accepted explanations for double quasar formation is that they arise from galactic mergers. In the distant universe, galaxies were much closer together and frequently collided, triggering massive bursts of star formation and fueling the growth of supermassive black holes at their centers. When two galaxies merge, their central black holes don't immediately combine. Instead, they enter a long and chaotic gravitational dance, gradually spiraling closer together over millions of years. During this process, both black holes can be actively accreting matter, becoming quasars simultaneously. This scenario explains why double quasars tend to be found in environments with significant amounts of gas and dust, remnants of their parent galaxies colliding and mixing together. However, not all double quasars necessarily result from galactic mergers. Some could be gravitationally bound pairs of black holes that form together in the same galaxy. This raises another possibility. Could double quasars be the early precursors to binary supermassive black holes that will eventually merge, producing some of the most powerful gravitational waves in the universe? If this is the case, then observing double quasars today gives us a glimpse into a process that will ultimately culminate in a cataclysmic black hole merger billions of years in the future. The idea that double quasars could be precursors to merging black holes is particularly exciting because it ties into one of the biggest recent discoveries in astrophysics: gravitational waves. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time, confirming a major prediction of Einstein's general relativity. These waves were produced by the merger of two stellar mass black holes, but astronomers believe that supermassive black hole mergers, on scales millions or even billions of times more massive, should also produce gravitational waves. If double quasars truly represent black holes on the path to merging, they could be key targets for future gravitational wave observatories like LISA. But here's where things get even stranger. Some double quasars exhibit behavior that doesn't quite fit into our current models. In a few cases, the two quasars seem to be moving in ways that are difficult to explain through simple gravitational interactions. This has led some researchers to propose that at least some double quasars might not be pairs of black holes at all, but rather the result of exotic astrophysical effects, such as interactions with hidden dimensions or even wormholes. Could it be that some of these objects are connected through shortcuts in spacetime, allowing light to travel between them in unexpected ways? While there is no direct evidence for this yet, the mere possibility opens the door to some of the most profound questions about the nature of reality itself. Another bizarre aspect of double quasars is their potential link to time dilation. Because quasars are so far away, the light we see from them was emitted billions of years ago. But as the universe expands, time itself stretches, meaning that we are observing these quasars as they were in the deep past. Some researchers have speculated that certain double quasars might be optical illusions created by time dilation effects, where we are actually seeing the same quasar at two different points in time due to the way light is bent and delayed by intervening gravitational fields. If true, this would mean that some double quasars might not be twins at all, but rather echoes of the same object viewed from multiple vantage points across cosmic history. This leads to yet another mind-bending possibility. Could double quasars help us study the nature of time itself? Time is often thought of as a straightforward progression from past to future, but general relativity suggests that time is deeply intertwined with space, curving and bending in ways that defy intuition. If some double quasars are actually the same object seen at different moments in time, they could provide a unique way to study how time behaves on cosmic scales. They might even help us test theories that suggest time could flow in multiple directions or that certain regions of the universe might experience time at different rates. Another key mystery surrounding double quasars is their effect on their surroundings. Quasars are among the most energetic objects in the universe, capable of outshining entire galaxies. When two quasars exist in close proximity, their radiation can interact in unexpected ways, creating powerful shockwaves that ripple through intergalactic space. These interactions can shape the formation of new stars, trigger massive outflows of gas, and even influence the overall structure of the cosmic web, the vast, interconnected network of galaxies that stretches across the universe. Some scientists believe that double quasars could play a role in regulating the growth of galaxies, acting as cosmic engines that drive the evolution of entire galactic clusters. This brings us back to the question of dark matter. If dark matter is indeed responsible for holding galaxies together, then its distribution should influence how double quasars form and evolve. Some recent studies have suggested that double quasars might be more common in regions with high concentrations of dark matter, implying a deeper connection between these enigmatic objects and the unseen mass that pervades the cosmos. By mapping the locations of double quasars and comparing them to dark matter models, astronomers might be able to uncover new clues about what dark matter is and how it interacts with ordinary matter. At the same time, double quasars also challenge our understanding of black hole growth. Traditional models suggest that supermassive black holes grow slowly over billions of years by accreting gas and merging with other black holes. But some double quasars appear to be much more massive than expected for their age, suggesting that black holes might grow in ways we don't yet fully understand. Could there be alternative mechanisms for black hole formation, such as direct collapse models where black holes form without passing through a star-like phase? Could double quasars be evidence of primordial black holes, objects that formed in the earliest moments of the universe, long before galaxies even existed? These are the kinds of questions that make double quasars so compelling. Every time we find a new one, it adds another piece to the puzzle, challenging our assumptions and forcing us to rethink what we thought we knew about the universe. And with new telescopes and space missions on the horizon, the coming decades promise to be a golden age for double quasar research. We are only beginning to scratch the surface of what these objects can teach us, and the deeper we look, the more mysteries we uncover. Double quasars are more than just distant points of light. They are portals into the past, laboratories for testing the limits of physics, and windows into the fundamental nature of reality itself. They remind us that the universe is vast, complex, and full of surprises. And perhaps most importantly, they remind us that no matter how much we think we know, there is always more waiting to be discovered. The study of double quasars is more than just an exercise in cataloging cosmic oddities. It is a gateway to understanding some of the most fundamental processes that shape the universe. Every observation of a double quasar is like uncovering a fossil from the distant past, offering clues about how galaxies form, how black holes grow, and even how the universe itself evolves on the largest scales. But what makes these objects even more fascinating is that they challenge our understanding of physics in ways we are only beginning to grasp. One of the most striking features of double quasars is the way their gravitational fields interact. Each quasar is powered by a supermassive black hole, and when two of these colossal objects exist in close proximity, they influence each other in ways that defy simple Newtonian mechanics. The gravitational forces between them create complex orbital patterns that can warp spacetime itself, affecting everything from the way light bends around them to the way matter flows into their accretion disks. In some cases, this gravitational interaction may even produce secondary effects, such as jets of plasma that shoot out in opposite directions, forming massive cosmic beacons that can be detected across billions of light years. The presence of two quasars in close proximity also means that they compete for the same supply of interstellar gas. This can lead to an intense feeding frenzy, where both black holes rapidly accrete matter, growing at rates much faster than typical lone quasars. This rapid growth challenges existing models of black hole formation, suggesting that some black holes may reach supermassive status much earlier in the universe's history than previously thought. If this is true, it could have profound implications for our understanding of the early universe, potentially altering our estimates of when and how the first galaxies formed. One particularly intriguing question is whether double quasars can eventually merge into a single, even more massive black hole. If they do, the process would release an enormous amount of energy in the form of gravitational waves, ripples in spacetime that travel at the speed of light. While gravitational waves from stellar mass black hole mergers have already been detected, the merger of two supermassive black holes would produce waves on an entirely different scale, capable of shaking the very fabric of the universe. Upcoming space-based gravitational wave observatories, such as LISA, the Laser Interferometer Space Antenna, are expected to be able to detect these events, allowing us to witness black hole mergers on a cosmic scale for the first time in human history. But not all double quasars are destined to merge. In some cases, the two black holes may be moving fast enough that they remain in a stable orbit around each other indefinitely, locked in a gravitational dance that could last for billions of years. These systems could provide an invaluable opportunity to study black hole dynamics in a way that has never been possible before. By carefully monitoring their orbits and interactions, astronomers could test key predictions of general relativity, looking for subtle effects that might reveal new insights into the nature of gravity itself. Another major mystery surrounding double quasars is their role in shaping the large-scale structure of the universe. Quasars are among the most energetic objects in existence, and when two of them exist in close proximity, they can have an outsized influence on their surroundings. The intense radiation they emit can heat up intergalactic gas, preventing it from collapsing into new stars and effectively regulating the rate of star formation in their host galaxies. This process, known as quasar feedback, is thought to play a crucial role in galaxy evolution, but exactly how it works is still poorly understood. By studying double quasars, astronomers hope to gain a clearer picture of how black holes shape the cosmos on the largest scales. One possibility that has been proposed is that double quasars could be responsible for creating massive cosmic voids, regions of space that are almost completely devoid of galaxies. If a pair of quasars were active at the right time in cosmic history, their combined energy output could have been enough to blow away vast amounts of gas, preventing galaxies from forming in certain regions and leaving behind empty spaces that persist to this day. If true, this would mean that double quasars are not just passive objects but active architects of the universe's large-scale structure, influencing the distribution of matter on scales spanning millions of light years. Another strange aspect of double quasars is their potential connection to dark matter. Dark matter is an invisible substance that makes up the majority of the universe's mass, yet it does not interact with light in any detectable way. It is thought to be responsible for holding galaxies together, but its exact nature remains a mystery. Some researchers have speculated that double quasars might provide a way to study dark matter indirectly, by observing how their gravitational fields distort the light from background galaxies. This technique, known as gravitational lensing, could allow astronomers to map the distribution of dark matter in unprecedented detail, potentially leading to new breakthroughs in our understanding of this elusive substance. But perhaps the most mind-bending possibility is that some double quasars might not actually be separate objects at all. In certain cases, what appears to be a pair of quasars could instead be a single quasar whose light has been split into multiple images by the gravitational field of an intervening galaxy. This phenomenon, known as gravitational lensing, can create the illusion of multiple quasars where only one actually exists. If this is the case, then some of the double quasars we have observed might not be pairs of black holes at all, but rather optical illusions created by the warping of spacetime. This raises profound questions about the nature of observation itself. If our instruments can be tricked into seeing double where there is only one, how can we be sure that other cosmic phenomena are not similarly distorted? Could some of the most extreme objects in the universe be nothing more than echoes and reflections, artifacts of light bending around massive objects in ways we do not yet fully understand? If so, then double quasars could provide a unique opportunity to test our theories of spacetime, offering a new way to probe the warping of the universe on the largest scales. At the same time, the discovery of double quasars also raises questions about the ultimate fate of the universe. If black holes continue to grow and merge, will there come a point where they dominate the cosmos, swallowing up all remaining matter and energy? Could double quasars be the precursors to a future in which only supermassive black holes remain, drifting through an empty universe as the last remnants of a once vibrant cosmos? While this scenario remains speculative, it underscores the importance of understanding how these objects evolve over time. Double quasars are much more than just interesting astronomical curiosities. They are cosmic laboratories where the most extreme forces in the universe collide, pushing the boundaries of our understanding and challenging us to rethink what we thought we knew about black holes, galaxy formation, and the very fabric of spacetime. As our telescopes and instruments become more advanced, we will undoubtedly uncover even more about these enigmatic objects, revealing new surprises and deepening our understanding of the cosmos in ways we can scarcely imagine. For now, double quasars remain one of the greatest unsolved mysteries in astrophysics. But with every new observation, we take another step closer to unraveling their secrets. And in doing so, we move closer to answering some of the most fundamental questions about the nature of the universe itself. The mysteries surrounding double quasars stretch far beyond their gravitational interactions and impact on galactic evolution. They also hold the potential to unlock new insights into the earliest epochs of the universe. Since quasars are incredibly distant objects, the light we see from them today is often billions of years old, allowing us to peer into the past and witness the cosmos as it was during its formative stages. This makes double quasars invaluable time capsules, preserving a record of the conditions that existed when galaxies were first assembling. One of the most pressing questions in cosmology is how and when the first supermassive black holes formed. The standard model of black hole growth suggests that they begin as small stellar remnants and gradually accumulate mass over billions of years. However, the discovery of extremely massive quasars at very early cosmic times challenges this idea. Some of the quasars we observe today appear to have already reached colossal masses when the universe was less than a billion years old, a timescale that seems too short for conventional black hole growth mechanisms to explain. This is where double quasars become particularly intriguing. If two black holes exist in close proximity, they may accelerate each other's growth through a process known as dynamical friction. This occurs when the gravitational interactions between the black holes and the surrounding matter cause them to sink toward the center of their host galaxy, where the density of gas is highest. In such an environment, their accretion rates can skyrocket, allowing them to grow much faster than solitary black holes. If this mechanism is at play in double quasars, it could explain how some black holes became supermassive so quickly, potentially solving one of the biggest puzzles in astrophysics. Additionally, double quasars provide a unique opportunity to test alternative theories about black hole formation. Some researchers have proposed that rather than forming from the collapse of individual stars, supermassive black holes may have originated from the direct collapse of massive gas clouds in the early universe. If true, this could mean that black holes existed before galaxies, rather than forming within them. Observing double quasars in the early universe could help determine which of these scenarios is correct by revealing whether massive black holes were already present before significant galaxy formation had occurred. Beyond their role in black hole formation, double quasars also offer a window into the mysterious cosmic web, the vast, interconnected structure of galaxies, filaments, and voids that make up the universe. The distribution of matter on these large scales is influenced by dark matter, the invisible substance that provides the gravitational scaffolding for galaxy formation. Because quasars are so bright, they serve as excellent backlights, illuminating the otherwise hidden structure of the cosmic web. When two quasars exist close together, their combined radiation can reveal fine details about the surrounding intergalactic medium, helping astronomers map the distribution of both ordinary and dark matter with unprecedented precision. Another fascinating aspect of double quasars is their role in producing gravitational waves. While smaller black holes merging within our own galaxy produce ripples in spacetime that we can detect using instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory, the merging of two supermassive black holes in a double quasar system would generate much larger and more powerful waves. These waves would be so immense that they could take millions of years to fully propagate through space. If we could detect them, they would provide a completely new way of observing the universe, allowing us to study the most extreme gravitational interactions directly rather than relying solely on light. The problem is that current gravitational wave detectors are not sensitive to the incredibly low-frequency waves produced by supermassive black hole mergers. However, upcoming space-based observatories like LISA could change that. If LISA successfully detects gravitational waves from merging double quasars, it would confirm that these objects play a key role in shaping the cosmic landscape, providing the first direct evidence of black hole mergers on the largest scales. There is also the possibility that some double quasars might be linked to exotic forms of matter and energy. For instance, some theoretical models suggest that certain quasars might not be powered by ordinary black holes but by hypothetical objects like gravastars or boson stars, exotic entities that could challenge our fundamental understanding of spacetime. If any double quasars exhibit properties that deviate from standard black hole models, they could provide evidence for entirely new physics, potentially rewriting our theories of gravity and quantum mechanics. Furthermore, double quasars may offer new insights into the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. Since quasars are among the brightest objects in the cosmos, they can be used as standard candles, reference points for measuring cosmic distances. By studying the way double quasars shift over time, astronomers may be able to detect subtle changes in the rate of cosmic expansion, offering clues about whether dark energy has remained constant or evolved over time. The possibility that double quasars might be linked to cosmic strings, hypothetical one-dimensional defects in spacetime left over from the early universe, is another tantalizing idea. Some physicists have speculated that these strings could act as gravitational lenses, bending light in ways that could create the illusion of multiple quasars where there is actually only one. If this is true, then some of the double quasars we observe might not be pairs of black holes at all but instead distortions caused by ancient remnants of the Big Bang. In addition to their scientific significance, double quasars also raise profound philosophical questions about the nature of reality itself. The fact that we can see them at all is a reminder of just how vast and interconnected the universe truly is. The light from these objects has traveled for billions of years, crossing unimaginable distances to reach us. In some cases, we may be observing quasars that no longer even exist, their light serving as a ghostly record of a bygone era. This leads to the unsettling thought that our own galaxy may one day host a similar spectacle. If the Milky Way eventually collides with the Andromeda Galaxy, as current models predict, the supermassive black holes at the centers of both galaxies could form a double quasar of their own. If that happens, future civilizations, perhaps millions or even billions of years from now, might look up at the night sky and see a cosmic beacon unlike anything we have ever known. The study of double quasars is a testament to the power of human curiosity. With every new discovery, we push the boundaries of what we know, unraveling mysteries that seem beyond our reach. And yet, for every question we answer, new ones arise, reminding us that the universe is far more complex and wondrous than we could ever imagine. The implications of double quasars go far beyond their immediate gravitational interactions. They serve as cosmic laboratories, revealing fundamental truths about the structure and evolution of the universe. By studying them, scientists can probe the very fabric of spacetime, test theories about the early universe, and even challenge some of our deepest-held assumptions about reality. One of the most compelling questions double quasars raise is whether they are truly pairs of supermassive black holes or if some of them are merely illusions caused by gravitational lensing. Gravitational lensing occurs when the light from a distant object is bent by the gravitational field of a massive foreground object, such as a galaxy. This bending can create the illusion of multiple quasars where only one actually exists. In some cases, a single quasar may appear as two or even more distinct objects, separated by vast distances in the sky, but in reality, they are all images of the same source. This phenomenon, known as an Einstein cross, has been observed in multiple instances and is a crucial factor in the study of double quasars. To determine whether a double quasar is a true binary system or a result of gravitational lensing, astronomers rely on a combination of techniques. Spectroscopy, which analyzes the light emitted by these objects, can reveal subtle differences between the two sources. If the spectral lines of both quasars show identical characteristics and vary in brightness and perfect synchronization, it is likely that they are actually the same quasar, duplicated by lensing. However, if the spectral lines show different shifts or respond to changes in their environment independently, then the two quasars are likely genuine companions. This distinction is critical because true binary quasars provide unique insights into the nature of black hole mergers. When two supermassive black holes are on a collision course, they interact in ways that warp spacetime itself. As they spiral closer together, they create what is known as a binary in spiral, a slow, inevitable dance that releases enormous amounts of energy. Over time, this process accelerates, culminating in a violent merger that sends gravitational waves rippling across the cosmos. Such mergers are believed to be responsible for some of the most energetic events in the universe. When two black holes collide, they unleash more power in a fraction of a second than all the stars in the observable universe combined. The resulting burst of gravitational waves carries vital information about the nature of gravity, potentially allowing scientists to test Einstein's general theory of relativity in ways that were never before possible. If double quasars can be confirmed as true binary systems, they will serve as prime candidates for detecting these elusive signals, helping to unravel the mysteries of gravity on a cosmic scale. Another fascinating aspect of double quasars is the impact they have on their surrounding environment. When two quasars exist in close proximity, their combined radiation can have profound effects on nearby gas clouds and star-forming regions. The intense energy emitted by quasars is capable of stripping electrons from atoms, a process known as ionization. This can either trigger new waves of star formation by compressing gas clouds or, conversely, shut down star formation altogether by heating the surrounding gas to extreme temperatures, preventing it from cooling and condensing into new stars. This delicate balance between creation and destruction is a crucial factor in galaxy evolution. Some galaxies appear to have undergone periods of intense quasar activity, only to later become relatively dormant. It is possible that interactions between double quasars play a role in this transition, acting as cosmic regulators that dictate whether a galaxy continues to form new stars or enters a more passive phase. If so, the study of these objects could provide a deeper understanding of why some galaxies thrive while others fade into obscurity. The potential for double quasars to reveal hidden aspects of the universe doesn't end there. They may also provide clues about the nature of dark matter, the invisible substance that makes up most of the universe's mass. Although dark matter does not emit or absorb light, its presence can be inferred from its gravitational effects on visible objects. When two quasars exist close together, their combined gravitational influence can act as a natural detector for dark matter, allowing astronomers to map its distribution with greater accuracy than ever before. One method for doing this involves studying the way light from double quasars is distorted as it travels through space. If dark matter is present in significant amounts, It should create subtle gravitational lensing effects, warping the light from the quasars in ways that reveal its structure. By analyzing these distortions, scientists can construct detailed maps of dark matter's distribution, potentially unlocking one of the greatest mysteries in modern physics. The role of double quasars in testing alternative theories of gravity is another area of active research. While general relativity has stood the test of time, some physicists speculate that it may not be the final word on how gravity works, particularly on cosmic scales. Certain modified gravity theories propose that our understanding of gravitational interactions may need to be revised, especially in environments involving supermassive black holes. Since double quasars provide extreme test cases for gravitational physics, they could offer the first concrete evidence supporting or refuting these alternative models. In addition to their scientific significance, double quasars also capture the imagination because of what they represent: an unfiltered glimpse into the most chaotic and violent processes in the universe. Their immense power, their role in shaping galaxies, and their potential as beacons of cosmic evolution make them some of the most fascinating objects ever discovered. They remind us that the universe is far from a static place. It is an ever-changing, dynamic landscape where entire galaxies are torn apart, black holes collide in cataclysmic bursts of energy, and matter is transformed in ways that challenge our very understanding of physics. Looking ahead, the future of double quasar research holds incredible promise. With the advent of new telescopes like the James Webb Space Telescope, which is capable of peering deeper into the cosmos than ever before, scientists hope to discover even more examples of these rare objects. Additionally, upcoming gravitational wave observatories such as LISA, the Laser Interferometer Space Antenna, may finally be able to detect the gravitational ripples produced by merging double quasars, providing direct evidence of their impact on the universe. The search for double quasars is not just about understanding black holes, it is about unraveling the mysteries of the cosmos itself. These objects provide crucial insights into the nature of time, gravity, and the evolution of galaxies. They serve as cosmic lighthouses, illuminating the darkest and most enigmatic corners of the universe. And as technology continues to advance, we may one day uncover even more astonishing truths hidden within their light. Perhaps the most profound lesson double quasars teach us is that the universe is far more interconnected than we ever imagined. The forces at play in these distant, massive systems are the same ones that govern the motion of planets, the formation of stars, and even the fundamental laws that shape reality itself. In studying them, we are not just looking outward, we are also looking inward, seeking to understand our own place in this vast, ever-expanding cosmos. The journey to understanding double quasars is far from over. In fact, it may be just beginning. As telescopes become more powerful and detection methods more precise, astronomers are gaining the ability to study these objects in unprecedented detail. But with every new discovery, more questions arise. What triggers the formation of a binary quasar system? How do these immense black holes interact over time? Could they be responsible for some of the most dramatic events in the universe, such as the formation of supermassive black holes themselves? One of the most exciting possibilities is that double quasars could provide a direct window into the origins of the largest black holes in existence. We know that supermassive black holes lurk at the centers of nearly all large galaxies, but we still don't fully understand how they grow to such mind-boggling sizes. Some theories suggest that these monstrous objects form through the repeated mergers of smaller black holes over cosmic time. If this is the case, then double quasars, particularly those that are on the verge of merging, could serve as the missing link between small-scale black hole collisions and the gigantic supermassive black holes we see today. The idea is that when two galaxies collide, their central black holes do not immediately merge. Instead, they enter into a gravitational dance, spiraling around each other as they gradually lose energy. This slow process can take millions or even billions of years. During this time, both black holes can continue feeding on surrounding gas, creating the double quasar effect. But as they move closer together, they eventually reach a critical point where gravitational waves begin to carry away their orbital energy at an increasing rate. This final phase, known as the final plunge, happens in a fraction of the time compared to the entire merger process, and results in a massive burst of gravitational waves. If we could observe a double quasar in the late stages of this process, we would be witnessing one of the most powerful events in the universe: the birth of a single, even larger supermassive black hole. This is precisely why astronomers are searching for double quasars in various stages of evolution. Some may still be widely separated, while others could be in the final moments before their inevitable collision. If we can find a system where two quasars are in the last stages of their spiral, it could provide definitive proof of this black hole growth mechanism. Beyond their role in black hole mergers, double quasars may also be key players in the cosmic web, the vast structure of the universe itself. The universe is not just a random scattering of galaxies. Rather, it is arranged in a massive, interconnected network of filaments and voids. These filaments, made up of dark matter and gas, serve as highways along which galaxies form and evolve. Some researchers believe that double quasars could act as indicators of regions where galaxies are colliding and merging at a rapid rate, making them prime locations for studying large-scale cosmic evolution. Another remarkable feature of double quasars is their potential to reveal hidden properties of black holes. While we have made great strides in understanding how black holes behave, many mysteries remain. For instance, the existence of supermassive black holes in the early universe is difficult to explain under current models. Some quasars have been observed at distances so great that they must have formed within the first few 100 million years after the Big Bang. But how did they grow so fast? Could double quasars be part of the answer? One possibility is that the merging of smaller black holes in the early universe happened at a much faster rate than expected. If early galaxies frequently hosted double quasars, it could mean that black holes had an easier time growing to enormous sizes. Some scientists even suggest that double quasars could be a sign of an alternative formation mechanism for black holes, one that does not require the slow accretion of matter but instead relies on the direct collapse of massive gas clouds into black holes. This idea is intriguing because it could help resolve a long-standing cosmological puzzle. Why do some galaxies host such massive black holes while others do not? If double quasars were common in the early universe, then the growth of black holes may have been more chaotic and dynamic than we previously thought. Instead of black holes slowly forming in isolation, they may have been rapidly merging and consuming each other in a turbulent cosmic feeding frenzy. Observing double quasars could also help us understand one of the strangest phenomena in astrophysics: black hole spin. Every black hole has a spin, a measure of how fast it is rotating. This spin is determined by the history of how the black hole formed and grew. If a black hole has grown mainly by consuming gas that spirals in from a single direction, it will have a high spin. But if a black hole has experienced multiple chaotic mergers with other black holes, its spin may be much more random. By studying double quasars, astronomers can test different spin models and determine how black holes acquire their angular momentum. If two black holes in a double quasar system have aligned spins, it may suggest that they formed in a stable, ordered environment. But if their spins are completely misaligned, it could indicate a history of chaotic mergers and unpredictable interactions. Perhaps the most mind-bending question of all is whether double quasars could provide evidence for entirely new physics. Some theories suggest that extreme gravitational environments, such as those created by two supermassive black holes in close proximity, could reveal deviations from general relativity. If there are hidden aspects of gravity that we have yet to discover, double quasars might be the key to unlocking them. For example, some alternative gravity theories predict that merging black holes could produce exotic particles or even tiny wormholes that momentarily connect different parts of spacetime. If these effects exist, they might subtly alter the signals we receive from double quasars, allowing us to test whether our understanding of gravity is truly complete. Ultimately, double quasars are far more than just fascinating celestial objects. They are cosmic time capsules, carrying information from the dawn of the universe to the present day. They challenge our understanding of black holes, galaxy formation, dark matter, and even the nature of spacetime itself. Every new discovery brings us closer to answering some of the most profound questions in physics, yet also opens the door to new mysteries waiting to be solved. And with each passing year, our ability to study them improves. Future telescopes, both on Earth and in space, will allow us to probe these enigmatic systems with greater precision than ever before. Whether through direct observation of their light, gravitational wave signals from their mergers, or unexpected phenomena that defy explanation, double quasars will continue to push the boundaries of what we know. The universe is still hiding many of its secrets. But double quasars may hold some of the biggest clues to unlocking them. One day, they might even change the way we see the cosmos entirely. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.